Okay, good morning, everyone, or afternoon, evening, wherever you are. I hope you can hear me. My name is Markus Adas, and I'm going to chair today's Astro-particle physics and cosmology session. We have 9 talks in 3 blocks. The first 2 blocks will deal with physics of the early universe, primordial black holes, topological defects, scalar fields, and their cosmological implications. And then the third block will switch topic to recent observation of cosmic rays with AMS on board the International Space Station. So each talk is limited to 25 minutes, and this includes 5 minutes for questions. So I would like to ask the speakers to stay within this time limit. What else? Yeah, so questions can be asked after the talks. You can use the raise hand function in Zoom to indicate that you want to ask a question, and then I can assign speakers. You can also use the chat in Zoom if you want to ask a question or if your audio is not working. And there's also a Mattermost channel where you can have some follow-up discussion. So I suggest that you use these tools at your convenience. If there's going to be a longer discussion on some of the topics, we can break it up, and then there's a dedicated discussion session at the very end of today's session where we can wrap up. Okay, so this is all I wanted to say. Again, welcome. Attendance is a bit low at the moment, but this is probably due to the inconvenient time slot for the Americas. Let's hope that this is going to increase during the session. And the first speaker today is Hyun-Soon Lin. Can you start sharing your screen?
Sure. Okay, so greetings, everyone. Have you seen my screens? Have you all seen my screens?
Yes, you can start.
Okay, so greetings. My name is Hyun-Soon Lin. So I'm a postdoc from the Academic Silicon, Taiwan. So today's talk is based on my recent work with Professor Grady Min in the National Jiao Tong University. So all in all, the talk today is about how to constrain the isospin violating dark matter. The self-intending dark matter with isospin violation features by a very old neutron star. So I will tell you more later. Okay, so I divide my talk today into a few parts. So in part 1, I would like to briefly introduce the motivation for introducing dark matter self-interaction. And although in the later talk, I would like to focus on model-independent analysis, but I would like to also use a few slides to show you that our model-independent analysis is actually justified by well-motivated phenometrical models. So, and after part 1, I would like to change my target to the neutron star capture of dark matter particles. Although such kind of capture mechanism has been studied decades ago for the solar capture or for the Earth capture, but for the neutron star capture, there will be an additional effect called the polyblocking effect. So I would like to spend some time to discuss with such effect and its impact to the capture rate computation. And then follow up. So when the neutron star capture lots of dark matter particles inside it, so these dark matter particles could collapse into a black hole and destroy the entire star. So to understand such kind of mechanism is crucial to our later study on the neutron star sensitivity on dark matter parameters. So after all of these 4 parts, I will address a short summary. Okay, so let's move to the part 1. So there are plenty of evidences that support the existence of dark matter, such as from the galactic rotation curve, from the gravitational lensing effect. On the other hand, suppose the dark matter particles are collisionless. If we put this assumption into the embodied simulation, of course, the results agree with large scale structure observation very well. However, in the small scale structure, typically speaking, the scale smaller than a few megaparsec, there are some tensions between the simulation and the observation, such as Cole-Kasper problem, missing satellite problem, and too big to fail problem. So in order to resolve these problems between the simulation and observations, dark matter self-interaction is introduced. So under this assumption that dark matter particles are collisional instead of collisionless, so the energy can be transported between the dark matter particles. So the current astrophysical constraints on the dark matter self-interaction cross-section sigma chi is given, should lie within this range. So this will be a few introduction on the dark matter self-interaction. So on the other hand, there are plenty of terrestrial detectors are built to measure the direct interaction between the dark matter and the standard matter particles from the sub-GeV to GeV dark matter mass. And these are the current constraints on the dark matter baron interactions cross-section, as well as the dark matter electron cross-section. Also other constraints from the supernova, red giant, something like that. Okay, so this will be my introduction part on how why we need dark matter self-interaction, as well as the current status of dark matter direct detection. So let me move on to the phenometrical setup. So our phenometrical setup, we want to include such a feature that dark matter should self-interact and also interact with standard model particles. And we found that there's actually some well-motivated model called the W1D. So in this model, there are two new gauge bosons are introduced. One is a scalar boson. You can think that this is just like a dark Higgs. Another, the massive spin one vector boson, just like a dark photon. And in our framework, we assume that only dark matter left in the current universe. So it means that there is no anti-dark matter. So in that case, the scalar particle, the scalar boson is responsible for the attractive self-interaction, and the vector boson is responsible for the repulsive interaction. But in the later analysis, we will only focus on the attractive interaction dominant, the attractive interaction dominant range. So we will assume these purple conditions always hold. In that case, we can ignore the repulsive interaction in the dark sector. On the other hand, in addition, both new gauge boson can also couple to the standard model particle through the kinetic mixing as well as the mass mixing. In that case, we can assign effective Lagrangian for the dark matter baron interaction, such as the dark matter neutron interaction characterized by the epsilon n, and dark matter proton interaction. And based on this kind of phenometrical model, it naturally generates the asymmetric interaction strengths between the dark matter neutron and dark matter proton. So we call this effect the isospin violation. So this phenometrical model also includes the isospin violation effect. It means that dark matter neutron interaction is not necessarily the same as the dark matter proton interactions. They could be the same, but in general, this is not a necessary condition. So let's review what we have. So we have dark matter self-interaction mediated by the scalar boson, which is attractive. And we also have dark matter standard model interaction through the the two gauge bosons, and such model also induce the isospin violation effect, which the dark matter proton cross-section is not necessarily the same as the dark matter neutron cross-section sigma chi here. So this will be the introduction part. So let me move on to the next part, the neutrons, the capture mechanism of dark matter by a neutron star. So now imagine there is a neutron star circling around the Milky Way. So it constantly encounters lots of dark matter particles in the halo. So suppose there's one dark matter particle one dark matter particle gets attracted by the gravity of the star and falls into it. So let's see what will happen during its passage. So suppose this dark matter particle falls into the star and encounter other baryons here. I mean, dark matter can interact with can scatter with the baryon through the dark matter baryon interactions and transport enough energy to the baryon after the scattering. So eventually, if dark matter lost a significant kinetic energy, then it will be permanently trapped inside the star. So we call this is a neutron star capture of dark matter particle, or just a capture for short. So such kind of mechanism that dark matter particles captured by the stellar objects has been studied decades ago. However, in the neutron star case, there's one additional condition. That remember that most of the baryons inside the neutron star are in degenerate state. So if the dark matter particles cannot transport enough energy to the baryons and excited such baryons above the Fermi sea, then the scattering will not happen. So when dark matter particle carry the kinetic energy much less than the chemical potential of the stellar components such as neutron or baryon, there's only a small fraction of baryons close to the Fermi sea that can participate the scattering process. This is very different from the capture mechanism due to the sun or the earth. So such kind of effect is also called the Pauli blocking effect, and this significantly reduce the capture rate. So in this slide, I would like to show you the capture rate of dark matter particles by the neutron star. So this is let's focus on the left figure here. So the vertical is the capture rate, and horizontal is the dark matter mass. So this green line is the capture rate due to the contribution from the neutron capture inside the star. So you can see that when the dark matter mass is smaller than 1 GeV, the capture rate is suppressed, become a constant instead of rising up. So this is due to that when dark matter is smaller than 1 GeV, the kinetic energy it carried is much less than the chemical potential. So most of the baryons do not participate in scattering. So it suffers from a very severe suppression here. On the other hand, this red line is due to the capture rate contribution from the proton. So the difference is due to that the neutron ear is much larger than the proton ear. So the proton contribution is in general small in the isosphere symmetric case. On the other hand, let's look on the right plot. So this shows the isospin violation case that the sigma chi p is much larger than sigma chi n. Under this scenario, the contribution from proton is much larger than the contribution from the neutron. So the larger sigma chi p can compensate the small ears of neutron. So if in the presence of isospin violation, we cannot simply ignore the contribution from a proton to the capture rate. So we know how to capture the dark matter, how to compute the capture rate. Then we can compute the total number of dark matter particles n chi being captured inside the star in a given period. Say for example, in this talk, we will always choose the period is 5 giga-years. So this plot shows the total n chi, the total number of dark matter particles inside the star after 5 giga-year. So the blue line is a contribution from neutron, and the orange line is a contribution from the proton. So now we know how the dark matter number evolve in the neutron star. So let me move on to the next topic, that the black hole formation inside the star due to the captured dark matter particles. So now suppose in the beginning, in the early stage, only a few dark matter particles are captured inside the star. So these dark matter particles will reside in a small region close to the center of the star. And the size of the region is determined by the thermal radius. So the thermal radius can be obtained by solving the virial equations. So you see that the right-hand side is the gravitational potential from the neutron star itself, and the left-hand side is the kinetic energy of the dark matter particles. However, when there are more and more dark matter particles being captured inside the star, so eventually the dark matter self-gravity turn cannot be ignored. So if this turn becomes significant, then the thermal radius is no longer valid. Is no longer valid for this value here, because this term becomes larger and larger. So we have to take the dark matter self-gravity turn into consideration. So when this term becomes larger, then the radius, the thermal radius becomes smaller in order to rebalance this equation. So this means that the region for the dark matter residing in the star becomes smaller and smaller, becomes more and more compressed. So this is called the dark matter self-gravitating effect. So roughly estimated that the self-gravitating will be triggered when the dark matter self-gravity is comparable with the neutron star gravity here. So when the neutron star capture the dark matter number n chi across this threshold value, the dark matter triggers self-gravitating, and the size of this region becomes smaller and smaller. So it undergoes some gravitational contraction. So if there's no any force to stop this gravitational contraction, then all of the dark matter particles will collapse into a black hole. However, if dark matter is fermion, which is the particles in our work, so when the two fermion gets too close, the fermi degeneracy pressure will become more and more significant. So such kind of fermion degeneracy pressure generated from fermionic dark matter themselves can be a counterbalance to the gravitational contraction. So eventually, the collapse or the gravitational contraction will be stopped by the Fermi pressure generated by the dark matter themselves. So in order for the collapse to continue, we found that the neutron star must capture enough dark matter particles, which is given by this threshold value. So let me give you a number that suppose the dark matter particle is 1 GeV, then the neutron and put it into this equation, the neutron star must capture more than 0.1 solar mass in order for the dark matter self-gravity to overcome the neutron star. Overcome the Fermi pressure. But this will be very hard because the dark matter baron cross-section is highly constrained by the current direct search. So even the neutron star takes the entire age of the universe, it will be very hard for a neutron star to capture such huge amount of dark matter particles inside it. However, in the presence of dark matter self-interaction, particularly speaking for the attractive self-interaction, this self-interaction is an additional help to the gravitational contraction. So with attractive self-interaction, it will significantly reduce the number of dark matter particles being captured by the neutron star to overcome the Fermi pressure. So that's why we exclusively examine the attractive self-interaction case instead of a repulsive case. So if dark matter self-interaction is repulsive, then it will be more hard to collapse, for dark matter to collapse into a black hole. And this is the real expansion of the Yukawa potential. I'm not going to dive into these mathematical details. I'll simply skip it. So now let's temporarily ignore this complicated stuff in this slide and just focus on the last three conditions here. So now let me summarize in this part. For the captured dark matter particles to collapse into a black hole and consume the entire star, there are three conditions must be met. First, neutron star must capture enough dark matter particles n chi to trigger the dark matter self-gravitating. And when the self-gravitating is triggered, the dark matter number must large enough to overcome the Fermi pressure. So this counts the dark matter self-gravity as well as the attractive attractive self-interactions. And the third condition is that if the first two conditions are met, then this guarantee that the dark matter particles will collapse into a black hole. But when a black hole was born, there are two competing effects. One is the accretion rate, the other is a Hawking radiation. If the accretion rate is not larger enough, then the black hole will evaporate and left no trace of it, so the neutron star still feels fine. So in order for the black hole to grow up after its birth, the initial black hole mass, which translates to the total number of dark matter particles at the moment of collapse, should be also larger than a certain threshold number. So when these three conditions are met, then it guarantees that the entire neutron star will be destroyed by the dark matter, by the black hole due to the dark matter collapse, like this way. So now we have briefly reviewed the capture mechanism and how these captured dark matter particles collapse into a black hole. Let me show you the neutron star sensitivity on dark matter parameter space. So the idea to plot such a to survey such a sensitivity region is quite simple. So there must be a certain fraction of parameters in this space, that if we put the parameters in this shadier region into our framework, then our framework will tell us that the neutron star cannot survive longer than 5 gigayears because it already destroyed by the black hole due to dark matter collapse. However, if we search the sky and if we found that the neutron star lives longer enough, much older than this benchmark value, 5 gigayears, then we can further back and constrain, exclude this shadier region, because this the parameter within this shadier region tells us that the neutron star should be destroyed, and we cannot find it. However, if we find any neutron star lives longer enough, then we can constrain back here. So this plot shows the current neutron star sensitivity on the dark sector parameters such as the mediator mass and the dark matter mass, and the shadier region are already excluded for a 5 gigayear-old neutron star observation. Different color indicated different isospin violation value. So the light blue shaded region is a SIDM allow range, which I show you in the introduction part. On the other hand, not only the dark sector neutron star can also have the sensitivity on the dark matter Snellen model interaction, such as the sigma chi-n, the dark matter neutron in cross-section. So we can translate this back to the dark matter proton cross-section through the isospin violation value. So in this left plot, I would like to show you the neutron star sensitivity on the dark matter neutron cross-section for a given alpha chi and the dark matter and the scalar boson mass. So the pink shadier region is already excluded, and the solid line, dashed line, and the dotted line are due to different isospin violation value. So this shadier region is excluded by the neutron star observation, and the blue shadier region is the current result from the Dina-1 town. On the other hand, if we change the dark sector parameter, we make the scalar boson much more heavier, up to 10 MeV. The excluded range from the neutron star will become larger, and the neutron star also cover the range that cannot be covered by the current Dina-1 tau region. So we found that the neutron star also has a sensitivity on the dark matter Snellen interaction. Okay, so this is time limit. Let me summarize. So we found that neutron star acts as a complementary probe to other dark matter detection. The dark matter detection includes the dark matter direct detection and dark matter indirect detection. So neutron star is an additional ideal place to probe the dark matter parameters. And also we found that in the presence of isospin violation effect, the proton contribution to the capture rate cannot be ignored. And suppose dark matter in self-interaction is attractive, then it could become a black hole and destroy the very old neutron star. So by observing such old neutron star in the sky, we can constrain the dark matter parameters, no matter the parameters are in the dark sector only, or the parameter that bridges the dark matter and Snellen model sector. In this model independent analysis, we also provide a justification from a reasonable phenometrical model. So that would be my talk today. Thank you very much.
Thank you very much, Hyun-Sun. And the floor is open for questions. Again, if you want to ask a question, you can use the raise hand feature, or you can also post it in the chat. And I will also check MetaMost. So I can maybe start with one question. Maybe you said it at the beginning of the talk and I missed it, but how do you produce dark matter in this scenario? Is this thermally produced in the early universe by the kinetic mixing term?
In general, in this work, we did not survey such production of that dark matter in the early universe. We simply assume that dark matter just produced in the early universe and left to the present date. And those self-interaction and the dark matter Snell interaction are actually described by the dark UI model. So we didn't go through those production mechanism, but I think the production mechanism has been well studied in the recent literature with such kind of dark UI model. Yeah.
And can you maybe go back to your slide 21? So this was one of these days plots.
So
this one, yeah.
Okay.
Can you say here what generates these features in the blue shaded? It's like some resonance features.
I see. In general, we took this feature from a paper written, I think, written by Professor Yu Haipu in the maybe 2015 or something. That this feature is due to that if dark matter, the self-interaction is attractive, then for a two dark matter slowly gets closer and closer to each other, they may maybe have some resonance effect for these two dark matter particles to bound together by solving the Schrödinger equation. So this explains this spike behavior here. Yeah, but if the dark matter self-interaction is much weaker, such as the dark fine structural constant is much smaller, or even the dark matter self-interaction is repulsive, then this resonance effect, these spikes will disappear. Yeah.
Okay, thank you. I don't see any other questions. So yeah, thank you, Hyun-Sun.
Thank you very much.
And if you stop sharing your screen, then the next speaker can start sharing. And the next speaker is Takistov. I hope I pronounced this correctly.
Yeah, that's good.
Okay. If you start sharing.
Yes, 1 second.
It must be very late for you. Is that from Los Angeles, or where are you calling in?
That's right. It's okay. Let's see.
Okay.
Can you see the full? Oh, okay.
And we also see your red cursor there. Okay.
All right. Thank you very much for the opportunity to give this talk. My name is Vladimir Takhistov from UCLA, and I will tell you about programmable whole dark matter and ways to find it. So let me briefly give some general overview about PBH dark matter. So you have black holes that are astrophysical, generally, and these come from the old stars. And you also have black holes coming from the early universe. And this possibility has been pointed out already more than 50 years ago by Hawking and others. And these are primordial. And now the question is, why do you care about PBH dark matter? And there's several comments, and you can take them with various grains of salt. There's no clear signs of particle dark matter. And of course, we have very exciting various signatures, but none of them are fully convincing. We are now in the era of gravity wave astronomy, of course, with LIGO and so on. There are also PBH seem to appear quite generically in many BSM models. Of course, this is a model-dependent statement. They can help solve some astrophysical puzzles, such as seeds of supermassive black holes, and they actually can already appear in standard cosmology. Of course, this is very unlikely, but in principle, this is already a standard model candidate. So this is a nice point. So what is the status of PBH? And here is the summary from 2017 from a review by Sasaki and others. And as you can see, depending on the formation time and so on, PBH can span very many orders of magnitude. And there's many constraints already throughout the parameter space. So let me now focus briefly on this very important region of order solar mass and a little bit higher for LIGO, which is of course very exciting, and point out that there's many constraints and they depend on many uncertainties and so on. So it is important to study this region further. So let me now tell you briefly about the new robust constraint for LIGO PBH, and this comes from a paper from several weeks ago by myself and other collaborators, and this comes from PBH from gas heating. And the basic idea is that it's very simple, is that PBH traversing interstellar medium will interact with gas, right? And this means that the gas will be heated. And there are several generic gas heating mechanisms. One is dynamical friction, and this is on the right-hand side is a rough sketch. You have a PBH with an accretion disk. Here's gas, and as PBH is passing through, the gas is kind of pulled together, and this is the dynamical friction. And so this is one way to deposit energy. Then there's also photon emission. So accretion disk itself is quite hot, so it will emit photons that will also deposit energy into gas. And finally, there's also wind outflows. And what this means is that protons can also come out from the accretion, not just the photons, and they can also deposit heat. Okay. Now, with all these heating mechanisms, a great testing site would be a dark matter-rich dwarf galaxy with a lot of gas and dark matter, and a very good candidate is Leo T, which is very well studied. And then you can ask basically, will the how much is it cooling versus heating do you have, and then get a constraint. And this is a robust constraint, and this is independent of any cosmological assumptions. Okay, so that is always nice. And it turns out that the constraint is actually quite powerful and spans many orders of magnitude. And there are several lines depending on assumptions of accretion. But the point is that in the LIGO region, we now covered a little bit more of the parameter space, which is always of interest. Okay. So let me mention now what is happening in 2020 beyond just this constraint is that now if you look not just in the LIGO region, but in the top left corner of this plot, all these constraints are actually gone. And they're gone for various reasons, for example, in the femtolensing constraint, people didn't properly take into account the source effects, and that when the PBH becomes very small, you need to do diffraction optics and not just regular optics. I mean, you need to do wave optics and not just regular optics. And once you take these effects into account, it turns out the constraints are not there. Okay. So actually, right now, there's about 5 orders of magnitude open parameter space window where you can have PBH as all dark matter. And this is, of course, very exciting. So then next question is, how do you form PBH as dark matter? So in a, so to speak, standard PBH formation mechanism, you basically have a big perturbation, and it enters the horizon radiation era and then collapses. And here's a little schematic, right? So you have your perturbation, you enter the horizon, and then you collapse. Now, the issue is that in these, so to speak, standard constructions, you need to tune your infloton potential. And this can be seen from the fact that in the very simplest models of inflation, the single field inflation, the perturbations are basically scale invariant. So somehow you need to arrange that on a bigger scale, you agree with CMB observations. But then on a small scale, you somehow get a big perturbation to get the PBH. So to do this, you usually need to tune your model significantly, which is of course not very great. And the corollary of this statement is that if you have any restrictions on the behavior of the scalar field, then this will introduce problems of tuning. Okay. And as an example of this, just to illustrate, in a paper with Kawasaki, basically I showed that if you, for example, consider the recently proposed string swampland conjectures, which are effectively just restrictions on the potential of the scalar field, it is not so easy to get PBH in a very simple models of inflation. But this is just basically an illustration of this point that you need tuning. Okay. Now, let me now mention to you a new general alternative mechanism from scalar fragmentation. Now, scalar fields exist. You have the Higgs, and they're very generic in BSM models. And of course, from top-down theories, you expect many scalars also to appear. And in fact, in a typical SUSY-based models, you usually have order 100 scalars, which have very flat potential, so-called flat directions, and they often carry U1 charge, baryon or lepton charge. Now, after inflation, scalars, they have self-interactions, could break apart into pieces, solitonic pieces due to instabilities. And if you have a complex scalar, it goes to cuboles. If you have a real scalar, it goes to oscillons. It can be either a spectator field or the inflaton itself can break into pieces. Okay. And here's just a simulation schematic. So you start with a coherent condensate, you run your time, and then you see that you have stabilized lumps. And in fact, if you consider the gravity is the weakest force, and again, this is something that people have been discussing from a more formal perspective, we have shown together with collaborators that fragmentation is even more generic then. So these are comments about scalar fragmentation, but now what is the relationship with PBH? Well, the fragments are quite big, namely their percent of the horizon at formation, and they're quite stable. And since the process is random, you can imagine that there will be some overdensities in some regions of space. And these overdensities are totally unrelated to what happens with the inflation-regenerated big scale overdensities. And if some rare regions collapse, then you will get the PBH. And this has been originally suggested for cuboles in this PRL by Alex Kusenko and Eric Kotner. And then I suggested to also do this for oscillons. And then we had a more general analytic description with Sasaki. And here is just a schematic of cosmology. You have your radiation era. So you start with radiation. After the reheating, the inflaton decays, you have your radiation. Then there's also these cuboles from some other spectator field. And cubole scale is matter, so at some later time, they overcome radiation, and some of them collapse to PBH, and actually a very tiny fraction of them collapse to PBH. The others decay away, and so you're just left with black holes and radiation. Okay, so this is a general schematic of cosmology for such a proposal. And then depending on the various parameters that you stick in your model, you can arrange to get PBH in the interesting region of the dark matter, in the LIGO region, and so on. And what is another very interesting feature of this scenario is that because this is matter formation, you expect that as these pieces collapse, there is a lot of angular momentum, and so a big spin is possible for black holes. While in typical formation mechanisms, usually black holes that form do not have big spin. So this is a very nice feature, and not many mechanisms can accomplish this. And another thing I would like to point out is that, as you can see, the resulting spectrum was quite peaked for PBH. Okay, so this is PBH from scalar fragmentation. And now let me contrast this with another general formation mechanism from scalars. PBH from bubble multiverse. So what is happening here is that you start with a multi-field inflation, and again, motivated from various top-down constructions, you expect many scalars, so the inflaton potential could be argued that it is expected that it is quite complicated. And if the potential is quite complicated, if the shape of the potential is complicated, you expect many minima, okay, for the inflaton potential. Now, in that case, as your inflation is happening and you're slowly rolling down, you can encounter nearby minima to where you're rolling in the inflow tunnel. And then you can tunnel to them and you'll have vacuum bubbles. Now, the bubbles are broadly distributed in size. When the bubble forms, it expands, and depending on the formation time, there will be different sizes. Okay. Now, some bubbles are, there is some critical regime, and if the bubble overcomes this critical size, in fact, it could support inflation inside it, and so there will be a baby universe inside the bubble. So from the outside, you do not see it, but from the inside, some bubbles have very interesting behavior. Now, the bubbles expand during inflation and then later collapse. And so what happens is you will end up, because the bubbles are spread in size, you will have a PBHs with extended mass spectrum. And again, this is compared to the peaked spectrum I showed before. And what I just described is quite well known in the literature and has been studied by many experts, Sasaki, Vilenkin, and so on. And here is an example of a typical spectrum that you expect. So again, there is some critical regime of bubbles where you have this inflation inside in this baby universe. But the main point is you have this broad distribution. Okay, so you expect a flat shape, and you also then expect this decaying tail. And this is, again, in contrast to the peaked spectrum. So in this work from earlier this year, we had a fresh look again at this bubble multiverse. And here's an example of a two-field potential that we came up with, how this could happen. So you start, this is sort of a tilted Mexican head potential. You start at the top, you roll on the rim, and as you're passing right here, you can tunnel to the center. Then you roll farther, you stop tunneling, and then at the end you end up in the minimum. Okay, so this is just a schematic potential how this could happen. And what is more interesting is that if you form PBH dark matter from this mechanism in this open window, you will still have this extended tail because the distribution is expected to be broad. And then you can ask, how can you use this tail to indirectly probe dark matter in the open parameter window? So this provides an indirect test for such models. And in fact, what is very interesting is that HSC from Subaru has detected an event, and we fitted that event and showed that you can have PBH dark matter from bubble multiverse compatible with this event. So this is very exciting, of course, and very interesting. But in fact, you can do even better. In fact, you can generalize the model that I described in such a way that the spectra looks like this, and it's even more extended with additional features. And then you can simultaneously explain dark matter, HSC event, LIGO events, seeds of supermassive black holes together, like this. So you have dark matter right here, you have HSC, you have your LIGO, and then later on you have supermassive black holes. So this is super exciting because you basically have one model for all the observables. And what is more interesting is that HSC, as it will gain more, as it will observe things longer with more nights of observation, we have shown quantitatively that you will basically able to definitively falsify and test this scenario. Okay, and even more good news is that we actually have been awarded additional observation nights for the proposal, so this will be happening. Okay, that's great. So these are two different contrasting models that I have discussed, and again, one has a peaked spectrum, the other one was a more broader spectrum, and so there's different possibilities. Now, but the question is, can you peek a little bit farther into the open dark matter window itself, a bit more directly? And here I would like to advocate compact stars as primordial black hole laboratories, and this has some overlap with the nice previous talk for the particle dark matter. So in this scenario, you have these small PBHs in this open parameter window, and they could be captured by compact stars such as neutron stars or white dwarfs in dark matter-rich environments, such as the galactic center. Now, once captured, they will grow inside and it will destroy the star, and you can expect some exciting observables. So with Alex Kosenko and George Fuller, we showed that you can explain R-process nucleosynthesis, 511 keV galactic center axis, FRBs. And then in some additional follow-ups, I have also discussed that you can get solar mass black holes and some new GRBs. And let me just sketch these things for you now. And again, I will not go into too much detail, but just give you a flavor of what's happening. So consider millisecond pulsars, which are basically neutron stars that are rotating very fast. And they're really rotating near mass sharing limit. Now, once you stick in a black hole inside, the black hole will consume the star and the star will contract. And by the angular momentum conservation, it will spin up. And in that case, you can imagine that it's possible that there will be ejecta of material. Now, I would like to point out that more simulation studies are needed to confirm exactly how this is happening. And depending on what you stick into your simulations, different results come out. So so more studies are needed. But suppose that is the case, then this is a great site for R-process nucleosynthesis. And R-process nucleosynthesis is basically one of the dominant ways in astrophysics how you make heavy elements. Basically, you start with a seed nuclei, and if conditions are favorable enough, and you're in a neutron-rich environment, the neutrons are captured so quickly that you will be able to build up from a seed a high atomic number element. Okay, and on the right-hand side, you can see the distribution, and the peaks at the higher mass number are the R-process peaks, and one of them is gold. Okay. So this brings us to the point of making all the heavy elements with PBHs. Now, let me note that the abundance of the heavy elements is such that in the Milky Way, you have 10 to the 4 solar masses of them. But also, if you look in the ultra-faint dwarf galaxies, one of the 10 of them, namely reticulum-2, shows an excess. And it turns out that you can fit both of these things simultaneously, assuming the amount of ejecta that we found from analytical estimates. And now, in these estimates, there's very many astrophysical uncertainties that go in, so I would not advocate the right plot as a form of constraint, but rather as a statement that it is interesting that such systems, such laboratories can, in principle, contribute significantly. So what else we can do? Well, we can also explain 511 keV in the galactic center. So as I'm sure you know, and in the galactic center, for a long time, you already have been observing an excess in 511 keV, and is consistent with E plus annihilation. And the question is, where does this come from? And in fact, from the ejecta, from the expanding ejecta, there will be heating and positrons producing, and you can also fit to this excess and also explain. So that is also very nice. And in fact, together with the same authors, but also with David Radice, who's an expert in neutron star simulations, we have shown that you can actually explain 511 keV galactic center excess just with standard neutron star mergers without any BSM. Now, as I mentioned, I would like to advocate the view that these are very interesting laboratories for PBH, and there's possible exotic signals. And of course, things need to be confirmed with further studies, but let me sketch some of these signals. One of them is orphan kilonova. So kilonova is the afterglow of the ejecta. So for example, usually you have neutron star merger, material comes out, and there are nuclear processes that happen. And so you will see an afterglow hours and days after the event. And this is called the kilonova or macronova. Now, in the case of PBH NS, you will also experience this signal. However, the difference is that in the case of neutron star merger, you have an accompanying merger gravity wave signal because two neutron stars merged. But in case of PBH&S, you started with basically neutron star just sitting there, so there is no gravity wave from merger. And so you will have a kilonova without a accompanying gravity wave. So this is a interesting, unique signal to look for. Similarly, you can have a orphan GRB. So for short gamma ray bursts, the standard progenitor is a black hole plus disk. So you have your black hole, you have your accretion disk, the disk is accreted quickly, and the binding energy is then released. And then you have a short GRB. And this is basically what happens in a neutron star merger. Now, imagine that if the disk forms from PBH&S system, you could also then have such an orphan GRB, but it is orphaned because there is again no accompanying gravity waves. So this would be another type of signal to consider to look for. Further, you also have solar mass black holes that are formed late in cosmological time. And this is probably a more definitive signature of PBH, as I'm sure people know that in the astrophysics, you do not expect black holes below 2.5 solar masses. And the reason is this is basically the neutron star stability limit. Now, once you have a neutron star white dwarf and you stick inside the PBH and the PBH eats the thing, you'll end up with a solar mass black hole. And here's the schematic. But what is interesting in this particular scenario is that unlike usual scenarios which consider solar mass PBH, where the such PBHs are formed from the start, right here you have a population of very small, tiny primordial black holes that make up dark matter in this open window. But then you also have a subpopulation of solar mass black holes that formed late in the, at the cosmological times from small PBHs eating the neutron stars. So you have this interesting black hole distribution in your system. All right, so let me then summarize. So this is basically a Renaissance era in PBH research, and mainly because of its synergy with multi-messenger astronomy, such as, of course, gravity waves. And there's many new ideas for PBH formation detection, and I outlined several interesting possibilities. For formation from scalar field fragmentation, you will get a peaked spectrum, but you also can expect a big spin black holes, which you usually do not get from regular formation mechanisms. In the case, for example, if you do vacuum bubbles, you will have a broad spectrum distribution. And you can also explain many observables simultaneously, which is very nice. And again, with upcoming HSC observations, we will be able to test definitively if this scenario will be able to contribute to PBH dark matter in the open window. And further, I try to advocate that compact stars can serve as interesting PBH laboratories for a slew of possible null signatures. Now, of course, there's many open problems. The parameter space is very large and a lot of more work needs to be done. But of course, the hope is to get definitive statements about the role of primordial black holes in general. Thank you very much.
Yeah, thank you, Volodymyr, for this nice talk. It's very many very interesting concepts for the generation of primordial black holes and their test. So we have time for maybe one or two quick questions, and please use your raise hand feature on Zoom if you want to ask a question. I can maybe start again with one very early on. I think it was slide 6. You showed this extension of your parameter space in terms of, I think it was actually a later one. So you basically tried to extend this to lower mass black holes. I was under the impression that in this low mass region, you run into constraints coming from the evaporation of these primordial black holes. Is this taken into account here? This one, yeah.
Yeah. That's a very good question. So in this, I don't know why in this review they did not show, but you are correct. So the lower bound right here is set exactly by evaporation. So of course, to be dark matter, you want them to be right now, present right now. So there's a lower bound right here. As you correctly pointed out, there are a bunch of additional constraints here, but even several weeks ago, actually, there was a paper on gas heating, the one I described, but not for the solar mass black holes right here, but actually for the ones right here. But they are all cut off a little bit of parameter space right here, and there's still a very large space right here. So the answer is that yes, there is a little bit of parameter space missing right here, but the window is still there.
Okay, thanks. And yeah, maybe from the observational point of view in gravitational waves, can you think about future gravitational wave missions that are particularly useful to probe these the background of primordial black holes? I guess there will also be some features in terms of stochastic gravitational wave background that you can observe here.
I haven't thought particularly in detail about stochastic gravity wave background for these particular scenarios. Of course, the answer will depend on the formation mechanism. For example, if you look at the LIGO papers, what they're fitting to PBH depends on a particular formation model, right? Because you need to say how many binaries there are, how PBH form binaries, but this will depend basically on the cosmology and what you start with. So I don't have any particular comments to that, but I do want to say that one definitive feature that I briefly mentioned at the end, but also a lot of other people are advocating, are these smaller PBHs. Since you do not expect them in astrophysics, observing definitively a black hole of one solar mass would constitute to a lot of people a very strong evidence that this is PBH. Now, the issue is that LIGO by itself in gravity waves, as of right now, cannot easily distinguish is that a neutron star or a black hole. So if there's a 1.5 solar mass event, it's not clear which one is it. And this, the distinction comes in a higher order tidal deformability effects, which are not too sensitive. So that would be one particular thing to, if you can see, that would be great.
Okay, thank you. So I think we have to move on. Thank you, Volodymyr. And the next speaker, let me bring up my list here, is Anish Ghoshal. Are you on the call? Yeah. We cannot hear you. You have to unmute yourself.
Can you hear me?
Yes, we can hear you, and you can start sharing your screen.
Yes, just a moment, please.
So it's the green button on the Zoom.
Yes.
Yeah. Okay.
Hello.
Yeah. You can start. We see it.
Thank you. So I am Anish, and I'm going to talk about post-inflationary production of light dark sectors. And this is basically based on this work. Okay, so the outline of my talk is going to be the some kind of motivations for light dark sectors in particles physics. Then I will describe the preheating production of this in general from inflationary particle production. And then I'm going to talk about sterile neutrinos and cosmological bounds and how these light dark sectors come into play. And then show that how the inflationary particle production and this can be constrained by various observations from late time of observations from early universe inflationary observations. So this is the standard picture of the thermal history of the universe. We believe it started from a Big Bang and then it proceeds through the various stages of, and then it came into the radiation dominant universe at speed of it. from Big Bang nuclear synthesis. So, there are many motivated particle physics scenarios, especially the dark sector, which has got to do with dark matter and neutrino mass, and a whole dark sector has been postulated in order to account for this. And the idea of light dark sector comes in because of the fact that they are weakly interacting with the standard model particles, and the mediators are the ones that talk to via which the standard model particles talk to the dark sector. And there are many experiments, laboratory and cosmological, to search for these mediators. We have heard the talks of dark photon before in the earlier of this session. So, starting with the concept of inflation, we know that inflation solves the horizon problem, flatness problem, and fixes the initial fluctuation for galaxy and structure formation in lifetime of the universe. Usually, the picture goes like that. We have a scalar field. It slowly rolls down potential, and then creates this expansion. Expanding part time in the universe, which we observe at less time. Then the inflaton field basically transfers its energy to the visible sector, and that's basically called the particle, post-inflationary particle production. It can proceed perturbative through perturbative process. It can proceed through non-perturbative process. Right now in this talk, I'm going to concentrate on non-perturbative preheating, which is known as preheating. So basically, it's an oscillation kind of process. As the scalar field in inflaton rolls down in an FW background, the equation that it follows is known as the Matthew equation. And the solution of this scalar fields in terms of this creation and annihilation of operators is given in terms of this Fourier expansion. And these values are this AQ and Q are just some scaled variables in terms of the inflaton mass and some of the values of the potential, which I'm going to show later. So this equation is pretty hard to solve, and usually it's solved on lattice. This is the typical solution of the Matthew equation, where you can see the blue regions of the solution. So the two independent parameters are AK and Q. Q are basically represents various momentum modes, and AQ represents basically the fields. And these basically are the blue regions of the oscillative solutions, and the white regions are the exponentially growing solutions. So in terms of quantum physics, these oscillations can also be treated like particle production. And these white regions would essentially mean that for that kind of potential, for some kind of potential, there might be exponential particle production from the inflationary sector. And this especially happens because the inflaton is a bosonic candidate. And if you have other kind of particles, which here I just will go into these details of particle physics model later on. If it's a bosonic particle, it will have this particular feature of this exponential particle production. Just an example of the risk. If you have this kind of term where phi is the inflaton and chi is the particle that's the inflaton is getting produced from the inflaton, then this represents solutions of the chi. And you can see that with each growth, the solution goes with the different momentum modes. So this mixed quartic term will produce the particles, and they will grow due to what that is known as Bose enhancement during the preheating particle production. Okay, so let's keep this slide for the time being. Let's also keep this slide for the time being because I want to come to this later. Let's straight away go to some particle physics motivated scenarios. and one of them is a sterile, light sterile neutrino candidate. So we know that in standard model and also in case, I mean, neutrinos in general, they participate in flavor oscillation. It is represented in terms of the rotation matrix, which is known as the PNMS matrix. And if you do the transition probability calculation for the neutrino to oscillate between one flavor to another flavor, you usually end up with this combination of this PNMS, I mean, elements of the PNMS matrix. PNMS matrix are basically have some 6 unknown parameters which are usually constraints from the different oscillation experiments. And the 6 are basically the 3 mixing angles, one delta Cp, which violates Cp complex phase, and then the 2 mass differences between these 2 neutrino states. From the point of view of neutrino experiments, we have seen there are a lot of anomalies, especially in short baseline experiments. Some are from very high significance, and then if you do joint analysis with some of the experiments, the significance reduces or goes up. For example, if you do mini-boon and LSND, it goes to 6.1 sigma. An interesting point is and another interesting point I would point to that recently in last month also mini-boon presented results where actually this excess has stayed. So this excess, I mean, this sterile anomaly has been there for quite long. The LSND anomaly has been there for over 15 years now. But recently also they have observed this mini-boon excess with a very high statistical significance. However, there are some problems, and I was going to show general fit in the next slide. So although debatable in just 3 standard model neutrino plus 1 sterile neutrino framework, a light addition sterile neutrino with some mixing angle is still favored. So this is the global picture from all non-neutrino oscillation experiments. This is the mixing angle versus the sterile neutrino mass squared difference. You can see the predictions from various experiments, and basically the star is the best fit from all experiments. So already you can see there are some tensions between the different experiments. So here for this talk, I'm going to assume that we have a sterile neutrino candidate of a mass at around 1 EV, I mean EV scale mass, and let's proceed to see the cosmology. So in cosmology, the problem comes in because if you have such a EV scale neutrino, it basically contributes to the effective dark radiation. And the 2 observables that come from cosmology are basically the total mass of the neutrinos as normalized with this critical value, and then the ineffective, which are essentially the degrees of freedom or the dark radiation. And essentially, if you change of these values, then it essentially affects BBN through the fact that it changes the Hubble expansion. So the decoupling and the formation and decoupling of the various nucleons will be affected. So you really have some numbers, I mean, some constraint on this, and it cannot be much larger or much smaller than that. In the CMB, something same happens. You basically change the matter radiation inequality. If you change the ineffective, and basically it contributes to the predictions of the CMB, the peaks of the power spectrum. For large scale structure, basically this observable affects because it cuts the neutrino free streaming. If you have more massive neutrinos, or it basically cuts, and galaxies would not have been formed. There is some question from that. So instead of so these are basically the 2 values quoted from this. Might not be the latest values, but the order of magnitude is same. So any BSM physics that you do should respect these bounds. Now the fact is that if you have a 1 EV neutrino, then it readily contributes at 1. So you have to be save the sterile neutrino picture, and usually this is done by involving some kind of secret interaction within the sterile neutrino sector. And this secret interaction has been studied by many groups. Some have studied pseudoscalar interactions, some have studied vector interactions. So what happens is basically you create matter-like effects due to this new interaction. And when these neutrinos are produced in early universe through Donaldson withdrawal mechanism or sheaf polar mechanism or some kind of oscillation mechanism, this extra interaction basically stops due to creating of this matter-like effects and stops the oscillation and suppresses the Boltzmann production. And typically there are two key parameters: the coupling strength of this interaction versus mass of this mediator. And if you are within this region of the coupling strength and the mass of this mediator, which here I call it to be chi, you basically can save the solution. However, the important aspect here is that you have to consider the density, the primordial density of this chi bosons to be almost negligible to avoid this one, or others they themselves will contribute to the ineffective decrease of freedom. And this is non-trivial from the sense that I already showed you that if you complete the picture with the inflation and the particle production from inflation, then bosonic mediator would get both enhanced kick, and it is very difficult to keep the primordial density of these particles to be negligible. So what we did was we took a very simplified model where we had the phi as the inflection, chi as this particle, and we also have the Higgs. So chi is basically the dark sector. The inflection gives us inflation, then it decays, or it oscillates to give the dark sector, and then the dark sector is formed from the chi, and it also oscillates to give the Higgs sector, and the visible sector is formed from the Higgs. So now we have this problem. Now let's go back to the slide select. So one thing that we found out that if you have a quartic self interaction among the dark sector, then these growing modes are essentially stopped. And it basically is because this term acts like the effective mass term during the oscillation, and it contributes in this manner to the equation, and this is known as, we call it as quartic blocking. So it becomes more and more difficult to produce these chi particles if you have this lambda chi to be more and more. I mean, if you have more self interaction among the dark sector, it's very difficult to produce particles. So we wanted to use this. We wanted to use this property to save the sterile neutrino solution of the early universe from the early universe cosmology. This is just a plot. We solved the Matthew equation on lattice using this code. And this is a plot of the energy density that is shifted to the dark sector. I mean, normalized to with respect to the total energy density of the sector. And you can see, so this is just some time scaled in some manner. And you can see as time progresses, there is an exponential production. I mean, shift of energy density, or rather transfer of energy density from the inflection sector to the chi sector. And and by tuning these values of lambda chi, you can see this transfer goes down. So basically, I'm increasing lambda chi values and the transfer goes down. So now let's go back to what we were discussing. Now, with this property in mind, we chose a typical, very simple potential. We can, one can do with very proper UV complete potential. We just took a quartic potential. We have a mixing with the visible sector. We are mixing with the dark sector, and some of the parameters of the potential needed to be fixed from thermalization condition. Some potential needs to be fixed from CMB observable. Some of these parameters need to fix needed to be set. To neglect other kind of interaction. So also from there are isocurvature bounds which we looked into. So instead of going to details, let me just straight away go to the results. So here you can see this is the result that which we were trying to see. So if you have such an inflationary scenario, And if those particles are produced, those light bosonic particles are produced, then you can see by, so this is a plot of n effective versus delta chi. The gray region is basically ruled out from cosmology. And you can see that for some values, for certain values of the parameter models, by choosing this lambda chi, you can, at very low values, for example, if the lambda chi would not have been present, 0, then this is ruled out. But by suitably choosing lambda chi, you can see as I increase there, some of these solutions, I mean, some of these models, if I call each values to be one model, are basically rescued due to this quartic blocking. So this was the case for the stellar neutrino. The same thing can be done for a dark matter case. Dark matter basically it is like a non-thermal production of dark matter. Instead of producing the chi's, we call the chi to be the dark matter. But then the observable that you match in the dark matter sector is not n effective, but the dark matter relic density. So there you can do this. You can play the same game and you just match with the relic density. You produce it in the early universe, run through the FRW expansion, and you call it to be the dark matter produced from. And you also satisfy all the bounds. However, there are some problems. I do not have the time to go into details of the dark matter sector, but this is, I just wanted to point out that this is a new production mechanism of non-thermal dark matter. Now, let me just conclude. So we see that particle production of scalar fields during preheating can be suppressed with a quartic interaction term. Stellar neutrino solution, which is observed from various neutrino anomalies, can be saved due to presence of this light chi particles. These secret interactions involving with the help of chi blocks this production, stellar production in early universe, thus saving the cosmology. However, we also need to be in the right parameter space in the inflation model, namely we need to have the right quartic self-interaction, so that the whole early universe cosmology and late universe cosmology makes a viable picture. For the non-thermal, this is just a new production, a novel production mechanism from preheating one can consider. However, there is, as usual, there's a huge transfer of energy density from the infinite sector to the dark sector. In order to satisfy the relic, the quartic blocking or late time inflaton decay into the visible sector has to be taken into account more carefully. And usually one needs to invoke some kind of non-standard evolution like cannibalism to make the whole picture, I mean, basically to satisfy the density, because there is a huge particle production and there is no way, I mean, in spite of using the quartic blocking, you need one more mechanism to satisfy the relic. And I just want to conclude that this picture will also generate the gravitational waves from the tensor part of the matter. And this is what we are presently studying. Thank you.
Okay, thank you, Anish. Are there questions? Please use your raise hand feature on Zoom. Or you can also post the questions in the chat or on MetaMost. Okay, everyone is satisfied. Maybe let me ask one question.
Sure.
So your model is, so your focus on electron volt sterile neutrinos motivated by short baseline anomalies. Yes. Is it feasible to extend this also to other mass ranges? I mean, we also have some hints of possible sterile neutrino candidates in the KeV range from X-ray data. Would this be tunable to different energy mass ranges?
Yes, that's true. You're correct. So the KeV mass range, we took the EV mass range precisely because the cosmology is hugely affected. So for example, if you go beyond MEV sterile neutrino, then the cosmology is trivial, right? I mean, because then sterile neutrino does not thermalized at all. So from the EV to KEV range, as you are speaking, it's interesting to study because the cosmology has to be saved by invoking some kind of dark sector or some other technology, which is the central, which plays the central role for this connection between inflation and late time termination.
Thank you. Okay, I don't see any other questions. Then thank you, Anish, and also the other speakers of this first block. And we will have now a break until, what is it, 5 minutes to 10, where we are going to reconvene. So see you in a bit.
Just a test code. Okay.
If you can try.
Okay, I will try to share my screen.
Yeah.
I see.
That works.
Okay, thank you.
Hello, test code from my side too.
Yeah, Alex, please. You're also the first speaker in the next block. Yeah, that's good.
Okay, thanks.
Okay, hello everyone. Welcome back to the Astro-particle physics and cosmology session. For those of you who have not been in the first session this morning, if you want to ask questions after the talk, please use the raise hand option in Zoom, or you can also post questions in the Zoom chat, or you use the Mattermost discussion channel, and here on the slide, you also see the link here to this chat. So maybe Alex, if you can start sharing your screen.
Hello.
Okay, and I think we can get started.
Okay.
Yeah, looks good.
Okay. So first, I would like to thank the organizer for giving me the possibility to give this talk. So I will discuss the case of primordial Kerr rotating black holes, which is basically work which has been done in collaboration with Jérémy Offinger and Josik. Black holes, in fact, are now observed. In fact, basically, we have three types of black holes which have been discovered. The first kind are stellar black holes, which are well now observed with LIGO, Virgo. The black holes which originated, in fact, in the explosion of supernovae, of massive stars, with masses, let's say, starting from 3 solar masses to 100 solar masses. We know also that we have supermassive black holes at the center of galaxies with masses between 1 million solar masses and 10 to the 9, 1 billion or more solar masses. We also know that we have intermediate mass black holes that have been recently discovered with intermediate masses between 1,000 and 1 million solar masses. The mechanism for the formation of these black holes are, let's say, probably different. We don't know well how intermediate mass black holes and supermassive black holes are formed. Stellar black holes in general are formed from the explosion of stars or maybe from the merger of neutron stars, etc. Primordial black holes, on the other hand, are not formed from star collapse, but they find their origin at the beginning of the universe. They are primordial. They come maybe from inflation or the end of inflation, right after inflation. So maybe there were very large primordial overdensities which collapsed. Maybe there were phase transitions where the black holes were formed, or there could have been collapse of cosmic strings, of domain walls, or other objects, etc. If one assumes that one primordial black hole is formed in one Hubble volume in the early universe, one can show, in fact, that the mass of the primordial black hole is related to the time, the cosmological time at which they were created. So time 0 is the beginning of the Friedmann-Lemaitre universe, and one can show so the mass is proportional to this time, and the factor is 10 to the 38 grams. For example, if one take the time as being the Planck time, 10 to the minus 43 seconds, one can find the black hole mass, which is equal, in fact, to the Planck mass, that is 10 to the minus 5 grams. We can speak of Planck black holes, and we can consider right now that they are the lightest possible black holes. If, on the other hand, one considers black holes of masses 10 to the 15 grams, they were formed at a time of 10 to the minus 23 seconds. In fact, these black holes are the lightest possible black holes which are currently still existing, because if the mass of the black holes is smaller than 10 to the 15 grams, the black hole would have vanished much before the current time. If one considers black holes which could have been formed at the time of Big Bang nucleosynthesis at around 1 second, the mass of such black holes could be as high as 10 to the 5 solar masses. So they could be intermediate mass black holes, or maybe, in fact, seeds for supermassive black holes. For my discussion, I want to discuss the case of angular momentum. As for neutron stars, black holes can have an angular momentum, which is here called J, just J. And one generally defines the dimensionless parameter A star for black holes, which is J over the mass squared. With this definition, A is between 0 and 1. 0 is a Schwarzschild black hole, that is no rotation, no angular momentum, and 1 is an extremal Kerr black hole, the maximal possible angular momentum. Now about their formation. For the spin in a standard inflationary model, in general, one considers that there is a low spin. And that is, for example, on the left plot from Di Luca et al., it is shown that the spin of black holes, A star, is less than 10 to the minus 2 in general. But if you have a transient matter domination in the primordial universe, it can lead to a very high spin. On the right plot, in fact, from Harada et al., you can see that that A star can be as high as 1, depending on the model. So it is possible to have very high spin primordial black holes. Now, what is interesting with primordial black holes is that they are good dark matter candidates. In fact, they are plausible because it's very easy. You need no new extension to the standard model of particle physics. You don't need to extend general relativity. You just work with what you have at hand. Also, black holes are dynamically cold, so it constitutes cold dark matter. We know that they exist somehow, let's say. And there are still mass ranges possible for the black holes to represent all of dark matter. I am showing you this plot from Carr and Kuhnel, which is a very recent plot showing the current constraints on primordial black holes. You have on the y-axis the fraction of primordial black holes relative to the dark matter density. 1, it means that black holes constitute the whole dark matter as a function of the mass. All the colored region correspond to constraints that we have, which are more or less robust, in fact. But basically, the red one correspond to the evaporation of black holes, meaning below these limits, black holes are not have vanished until now. Blue is gravitational lensing, accretion, etc. So we have many constraints, and the A, B, C, and D region are open windows where you can find a large fraction of black holes constituting dark matter. So in the following, I will discuss the A region where we have nearly no constraint, and the B region, which correspond to planet mass black holes, like Earth mass black hole, and C correspond to stellar black holes. So what is interesting with light black holes is that they emit Hawking radiation. Basically, the black hole horizons can interact with the quantum vacuum if you have, let's say, the usual picture is if you have a pair of particles coming from the fluctuation of the quantum vacuum, one particle of the pair can fall into the black hole and the other one can fight the gravitational well and leave the black hole, and it is, let's say, emitted as Hawking radiation. Then the vacuum will get back its energy. The potential well, gravitational well, in fact, will lose a bit of energy, and so the mass of the black hole will decrease. It is possible to compute, in fact, the emission of particles by a black hole by Hawking radiation. It was first on the calculation of Hawking about that. Here you have a formula about the rate of emission of standard model particles. And you see that you have a temperature term, E is the energy of one particle. The idea is similar, in fact, to Planck's black body radiation law. For a black hole, one speaks about a gray body, not black body, because there is some more absorption, but you have a temperature. And the temperature is given, the Hawking temperature is given by this formula. For a Schwarzschild non-rotating black hole, the formula is very easy. It's the inverse of the mass with the factor 8 pi. The temperature is an important parameter. because if you have a very high temperature, you could emit particles with very high masses. And the temperature is influenced, in fact, by the rotation of the black hole. So for example, here you have the temperature as a function of the mass. So you have light black holes about 10 to the 15 GeV. In blue, you have Schwarzschild non-rotating black hole. And in red, you have a nearly extremal Kerr black hole. So you see that the temperature is shifted down when, because in fact of the angular momentum. And if you would like to emit, for example, positrons and electrons, you see that if you have a massive 10 to the 16 gram extremal Kerr black holes, it will not emit electrons and positrons, but a Schwarzschild black hole would be able to emit them. So the emission of particles strongly depends, in fact, on the angular momentum. Also, there is an additional effect. There is what is called the super radiance effect, which is a kind of coupling between the black hole spin and the particle spin. And in fact, it was shown that Hawking radiation is enhanced for particles of spin 1 and 2. So here you have the emission of photons, spin 1 particles, as a function of the energy E of the particle. For a Schwarzschild black hole, you have the blue line. And for a Kerr black hole, you can have either the red if it's nearly extremal, or a green one in an intermediate solution. So there is a strong enhancement by orders of magnitude on the emission of particles. Because particles are emitted, energy is lost, the mass of the black hole decreases, and one can speak about vanishing of a black hole. Well, you can see on the left the lifetime of the black hole that you obtain by integrating over the emission of particles. So you have the lifetime of the black hole as a function of the mass of the black hole. You see here that you have the age of the universe, which means if a black hole has a mass which is larger than 10 to the 15 gram, it has a lifetime which is, let's say, about the age of the universe. You don't see with such a plot really the difference between Kerr and Schwarzschild black holes, but on the right, you can see more the difference. Here, in solid line, we show the evolution of the mass of the black hole as a function of the time. Well, on the left, you have the mass over the initial mass. You see that for Schwarzschild black hole, the mass decreases slowly. Then, in fact, the mass at the end decreases very fast. You can say at the end, you have a kind of bomb. Yes, it vanishes very fast. For Kerr black holes, you have the green and red lines. So the vanishing is faster by a factor 2, let's say. For the spin, the evolution of the spin is given in dotted line. So the spin is 0 for a Schwarzschild black hole, so it starts at 0 and stays at 0. And in fact, the spin decreases slowly, fast, and goes to 0 and then stay to 0. And the more the spin of the black hole is important, the faster the loss of the spin exists. So the question is it possible to have an extremal spin today after, in fact, 13 billion years? There exists a limit given by 4 about the spin of rotating black holes from disk accretion, from let's say, stellar black holes. This limit is 0.998. It's difficult for a black hole to have a star larger than this value from only disk accretion. But primordial black holes could have been created with a spin, an A star, which is very close to 1. So you have the value of 1 minus S star today as a function of the mass of the black hole for different starting value very close to 1. You see, in fact, that the larger, the heavier the black hole is, and the higher is the final value of A star. Basically, if you have a black hole with a mass larger than 10 to the 17 grams, they will keep, in fact, their very high angular momentum. So it's possible to have extremal spin today, well below, in fact, Ford limit. I will consider now the isotropic gamma ray background constraint. So the gamma ray background constraint comes from diffuse background, for example, and in addition, active galactic nuclei, gamma ray bursts, maybe dark matter annihilation, Hawking radiation. It has been well measured by different experiments. You have here the flux of energy of the gamma ray background as a function of the energy of the particle. So black holes can participate, in fact, to this IGRB. You have to integrate over the emission of radiation from cosmic microwave background until today, considering also the redshift for that. And you can obtain constraints from that. So when you have a Kerr black hole, the spin has two effects. It can enhance the luminosity because there is more emission of radiation, so stronger constraint, but at the same time, the temperature is reduced in Kerr black holes, so there is less emission of energies, and you get weaker constraints. So you have both effects which can compensate or not. Here, I show you the fraction of PBH over the dark matter density as a function of the mass. So we are in the window A that we had at the beginning. If we consider that all black holes have the same mass, you can obtain this plot. So in green, you have the constraint, the excluded region when you have no spin, and in light blue, let's say, you have what you get when you have a Kerr black hole. So the constraints are stronger when you have Kerr black holes and the region is more excluded. Now there is another effect. In general, one considers that all primordial black holes have the same mass, but it is probably not the case. We studied, in fact, on the width effect. So we consider the log normal distribution with a width sigma. So because of the width, you broaden, in fact, the emission spectrum, which leads to stronger constraints. And at the same time, you broaden the mass distribution, which leads to a larger dark matter total density, which weaken the constraints. So the upper left plot is monochromatic, and you then increase, in fact, sigma. And you see that the constraints are very different when you use, in fact, a large width equal to 1, in fact. It goes up to 10 to the 18 grams with such a large distribution. An important effect also is the fact that black holes can emit gravitons. They can emit all kinds of particles. So here you have the emission rate for spin 0, spin 1, 1/2, and spin 2 particles. So spin 2 is gravitons. So primordial black holes can emit gravitons and therefore gravitational waves. Now we study the emission of gravitational waves by primordial black holes. You have on the left plot the frequency of emission as a function of the mass. You have the sensitivity of LIGO, Virgo, and the future LISA and BBO experiments. You see that they are sensitive, in fact, to the frequency, which are very close to 10 to the 40 solar masses. So very, very massive black holes, supermassive black holes, in fact. So supermassive black holes emit at frequencies of the experiment that we have on Earth, or will have on Earth. Unfortunately, the flux is decreasing a lot when you increase the mass of the black hole. And when you have supermassive black holes, the flux of Hawking radiation is extremely low, and you have no chance to see this with the current sensitivities, and probably in the future too. But we can consider that gravitational waves can bring, in fact, information from the very early universe. In fact, very light primordial black holes, which have now vanished. So with masses well below, in fact, the 10 to the 15 gram. So they don't exist anymore, but they could have left imprints in the cosmological background of gravitational waves. So here, it's a preliminary plot about the density of gravitational waves as a function of the frequency for different masses of the black hole, starting at the Planck mass up to a mass of 10 to the 9 gram. So at Planck mass, we are before inflation. At 10 to the 9 gram, we have more massive black holes, which vanished well before, in fact, Big Bang nucleosynthesis. So you can see that for such 10 to the 9 gram black holes, you can have a very high density of primordial gravitational waves emitted, which is of the order of LISA and BBO sensitivity, but with with a frequency which is much, much higher. In any case, trying to discover Hawking radiation is important for gravitational waves, because if you discover gravitational waves emitted by Hawking radiation, you validate at the same time the existence of the gravity. Now, something, let's say, amusing, I would say. There have been studies which have shown that trans-Neptunian objects, TNOs, in fact, have anomalous orbits. And there is an excess in microlensing events in the solar system at a distance of, let's say, between 450 astronomical units up to 700. And there could be, in fact, a new planet there with a mass between 5 and 10 Earth masses. And there are many questions about that. Many people think that there may be a planet, and many people would like to check if it is the case. There has been a proposition by Scholz and Unwin that it may be a primordial black hole. In fact, it is exactly in the window B, the one with planet mass black holes. And we decided to check what is the Hawking radiation of such black holes. So we for sure don't know the spin, since we don't even know the mass and if it even exists. So you have here the emission rate as a function of the frequency. And you see that such primordial black holes with planet mass will emit with a frequency of the gigahertz. So radio wave, in fact. So we checked how much Hawking radiation we could see from Earth. So you have the flux as a function of the distance from the black hole. So you see that the distance are very small. In fact, the scale is very small because Hawking radiation is too weak to be seen from Earth. Whichever the case. It's the same for photons and for gravitational waves too. But if we had a black hole in the solar system, the possibility would be to send a probe to put it in orbit around the black hole and to study the emitted radio waves. It's possible maybe because it's radio waves, so you need to have an antenna. For gravitational waves, it would be more difficult, let's say. But there are many proposals to study far objects, because the problem is that this kind of object is very far from us. So with standard probes, you would need tens of years to go there, even more, in fact, maybe 100 years. But there are proposals to build very small satellites, very small probes with masses of the order of the gram, with a sail, a solar sail that you push with a laser. It's a proof of concept. If you want to have a look, it's a breakthrough Starshot project. And you can try, in fact, to send probes to see this kind of objects with such a project. Okay, I want to make some advertisement. So to generate the Hawking radiation spectrum, we have written a public code in C, which is completely public, open source, that you can download from the webpage, which is called Blackhawk. So it has the it is made to compute Hawking radiation for Schwarzschild and Kerr primordial black holes. It has all the primary spectra of standard model fundamental particles, but also the secondary spectra of stable particles, which have been hadronized, for example, with Pitya and Herwig. So you have protons, you have electrons, etc. It has extended mass functions, as I presented in my previous slides, but also spin distributions. It can simulate the time evolution of primordial black holes. And as I said, it's completely open and you can download it. Okay, I'm going to my conclusion. So the main result is that we studied, in fact, the evolution of primordial Kerr black holes and the constraint from the gamma ray background. We studied broad mass distributions. So it brings, in fact, new information on the exclusion. We know that there is still an open window for planet mass black holes, and maybe planet 9 exists and is a primordial black hole. So it's an open question. And I presented you quickly the black hole public code to compute Hawking radiation. So the perspective is to try to find new probes in order to close the remaining primordial black holes mass windows for all dark matter, or to discover, in fact, primordial black holes. There is the question about the possibility to use gravitational waves to find a new way to look at primordial black holes. We can maybe also use constraints from extrasolar planet searches to constrain small primordial black holes and try to find other constraints. Okay, thank you.
Okay, thank you, Alex. The floor is open for questions. Please use your raise hand feature or post the question in the chat. I can maybe start with some very basic question. So if I recall correctly, at least for classical gravitational wave emission, you need a time-dependent quadrupole moment. Is this in this Hawking radiation picture not the case?
No, it's not like that. In fact, it's a continuous emission of gravitational waves. So it's mostly for something like LISA. It's not for LIGO Virgo.
Yeah, so you see like a diffuse background of yes. All primordial, but for the emission you still need some time-dependent quadrupole moment from black hole interactions.
No, not here. In fact, it's in fact what we have is really the emission of gravitons, which are interpreted as gravitational waves.
So the Hawking radiation here.
Yes.
Okay. Are there other questions? Maybe one more question from my side. So you mentioned a test of photon in Hawking radiation and via comparison of measured photon backgrounds. Are you taking into account also the fact that these photon backgrounds are to some extent already modeled by astrophysical sources? I guess the limits that you derive there could be also pushed to more constraining values if you also include astrophysical backgrounds in these photon backgrounds.
Yes, we consider, in fact, we considered it in the standard way. So we removed the background that we considered as standard model background. Mm-hmm. But of course, in fact, you may have more sources that we do not consider here.
Okay, thank you.
Thank you.
I don't see any further question. Then thank you, Alex. And we move to the next speaker.
Hello.
Jean-François?
Yes. Hello. Did you hear me?
I can hear you, and we also see your slides. So whenever you're ready.
Okay. First, thanks to the organizer for allowing me to talk at ICHEP. I will present the work done with my PhD advisor, Alexander Bay, about scalar fields in cosmology and their constraints for Big Bang nucleosynthesis. Scalar fields appear in many cosmological models, in particular in order to provide explanation for dark energy and inflation, but also to emulate dark matter. An idea is to replace simultaneously dark matter, dark energy, and inflations by one single scalar field. In the early universe, such scalar fields are not strongly constrained, except by their impact on Big Bang nucleosynthesis through the observed abundance of the elements. In the first part, I will present fuzzy dark matter models in which a scalar field behaves like dark matter, quintessence models which can explain the recent accelerations of the expansion of the universe, and dark fluid models which unify dark energy and dark matter with the same and unique scalar fields. In a second part, I will talk about the triple unifications, not only of dark energy and dark matter, but also inflation. The model assumes a non-minimal coupling to the gravity and a spontaneous symmetry breaking before inflation. After inflation, the scalar fields behave like in the dark fluid model. In the last part, we will derive the constraints on a stable and decaying scalar field from Big Bang nucleosynthesis. Let me begin with a quick reminder about the evolutions of scalar fields in cosmology. For an isotropic and homogeneous universe described by the Robertson and Walker metric, the Einstein equations are given by these two first equations and the Clyde-Gordon by the third one. In these equations, the universe is composed of a scalar field, phi, and other mean radiations and baryonic matter. For power law potentials, when the scalar field oscillates around its minimum, the average of the energy density is simply a power law of the scale factor. For example, if n is equal to 2, in other words, a quadratic terms for the potential, the density will evolve like matter. For n equal to 4, the density will evolve like radiations. But these results are only valid when the scalar field oscillates quickly around its minimum. During BBN, the scalar fields evolve differently, and we will see how for fuzzy dark matter models and quintessence models. So, first, discussions on cosmological scalar fields. The fuzzy dark matter models aims at explaining dark matter with the scalar fields corresponding to an ultralight particle. M is approximately equal to 10 power minus 22 electron volt. It is really tiny, but this value comes directly from the quantum wavelength. At galactic scale, the scalar fields form Bose-Einstein condensate, which made constitute galaxy-sized dark matter halos. For a typical halo of 10 kiloparsec, the quantum wavelength requires a mass with this kind of value as given by this formula. The fuzzy dark matter model has been studied in the context of galactic halos, and it can reproduce the flat spiral galaxy rotation curves. Another important result of this model is a solitonic behavior during head-on collisions between two galaxies, which is compatible with the bullet cluster observation. Furthermore, this model avoids the CUPC halo and missing satellite problems. I will discuss now the cosmological evolutions of fuzzy dark matter. The simplest model is a scalar field with a quadratic potential. The universe is composed of radiations, baryonic matter, cosmological constant, and a scalar field, which replace cold dark matter in the lambda CDM models. We can see the energy density fractions evolutions in these figures as a function of the scale factor. When the scalar field evolution is dominating by its kinetic energy, the density decays as a power minus 6. Later, the potential is no longer negligible, and we can see a plateau. When the scalar field oscillates quickly around its minimum, the energy density decays as a power minus 3 and as a dark matter behavior. The initial value of time derivative of phi can be chosen arbitrarily and impact the value of the energy density during the first step. And initial value of phi is taken to reproduce the dark energy density of cold dark matter. The potentials of this model is still an open question. There is no strong constraints given by the observations in the earlier universe. We can add a quadratic term in the potential. In this case, the difference is the eighth of the plateau and decay as a power minus 4. Planck data set a limit on lambda as given by this formula. Finally, the fuzzy dark matter models based on scalar fields can provide an explanation for cold dark matter. Cosmological scalar fields are also often used to mimic dark energy like incandescence model. In such models, the cosmological constant is set to 0 and replaced by a scalar field. Since all cosmological observations are currently compatible with a simple cosmological constant, the main features of such scenarios is a scalar field close to the dark energy value in the present universe, with an equation of state close to -1. For a tracking model characterized by the inverse power law potential, the equation of states is shown in these figures as a function of the scale factor. And we can see that P equal to 1 is excluded because the equation of state is not enough close to -1 today. P must be smaller than 0.105. The difference with the lambda CDM models is that the energy density of the scalar fields is expected to evolve and could have played a role at early stage of the expansion of the universe. To conclude, quintessence models based on scalar fields can replace the cosmological constants. The dark fluid model aims at unifying dark matter and dark energy with a single scalar field. The potentials of the simple dark fluid models is given by a constant. We could reproduce the dark energy with a value directly given by the cosmological constant and quadratic terms, which could replace cold dark matter like in the fuzzy dark matter model. One can modify this potential by adding, for example, an exponential in front of the constant. As we can see in these figures, the universe is composed of radiations, baryonic matter, and scalar fields. One scalar field which replace dark matter and dark energy. So, in dark fluid models, single scalar fields can replace both dark matter and dark energy simultaneously. In these sections, we will build a model in which inflation can be simultaneously explained within a dark fluid model. Details about this model can be found in this article. Scalar fields are ubiquitous in cosmology. One possibility to reduce their number is to unify dark energy, fuzzy dark matter, and inflations, which can all be described by scalar fields. We have already seen that dark fluid models replace dark energy and dark matter by a single scalar field. Another possibility is to unify inflations and dark energy, which lead to two stages of accelerating expansion. A third possibility is to unify inflation and dark matter, which can come from the incomplete decay of inflation. In such model, the standard chaotic inflation scalar field survives with a mass which is 6 orders of magnitude smaller than the Planck mass. Several models of triple unifications have already studied, but this model do not explain dark matter as in the fuzzy dark matter model. I will now present a more natural triple unification scenario by assuming a non-minimal coupling to the gravity and symmetry breaking before inflation. The model is defined by this action. The action here is invariant under Z2 symmetry. For phi equal to 0, the potential has a local maximum. Therefore, the theory is unstable around this value. The two minima correspond to phi equal to plus v and minus v. When the scalar field goes to one of these minima, the Z2 symmetry is spontaneously broken. Psi is the variation of the scalar fields around this the minimum. After the symmetry breaking, by replacing phi by psi, the action is given by this one. So, after symmetry breaking, if we neglect the scalar field variation psi, only the R and R square terms have an impact on the universe evolution. The R square term produce an inflationary period which will be similar to one of the Star-Rubinski inflation. This action can be transformed into the ancient frame where the R square degree of freedom is interpreted as a scalar field. In the ancient frame, we find several inflations, which is compatible with the cosmological microwave background. The amplitude of the power spectrum fixes the constant alpha wave square to 10 power 9. The inflation period starts at psi equal to phi Planck mass and end at phi psi equal to 1 Planck mass. After inflation, the inflaton decays into radiations and creates the scalar field chi. The scalar field psi, which appear after the symmetry breaking and characterize the variation around the minimum, will evolve as in the simplest dark fluid model when neglecting the higher order terms of the potential. The scalar fields replace dark energy thanks to the V0 constant and dark matter thanks to the mass term. The Xc3 and Xc4 terms have negligible effect. This can be seen in these figures. For example, the average the dark matter density in galaxies is obtained for a value of psi larger than 10 power 22 electron volt. And in this case, the Xi3 terms is 7 order of magnitude smaller than the mass term, and the Xi4 terms is 14 order of magnitude smaller than the mass term. So, the model that I presented can unify dark energy, dark matter, and inflations with only one scalar field. With all these scalar fields, the observed abundance of the elements can be modified. In the following, we will derive the constraints on the scalar field scenario from Big Bang nucleosynthesis. These constraints are detailed in this article. Big Bang nucleosynthesis is generally considered to occur during radiation dominations. The total energy density mainly composed of photons, electrons, positrons, baryons, neutrinos, antineutrinos, and dark matter. For a temperature of about 1 megaelectronvolt, the hydrogen nuclei can fuse into helium nuclei. The main process are shown in these figures. These reactions freeze out because of the universe expansion. The observational measurements give this limit on the abundances. In the standard cosmological models, the theoretical predictions obtained using alter BBN, publical, for example, are given here. The helium-4, helium-3, and deuterium abundances are compatible with measurement. But there is a conflict with lithium-7 abundance. In this part, we will discuss the theoretical predictions when adding a scalar field to the total energy density. The density of the scalar field is taken as a power law of the scale factor and modifies the abundance of the elements via modifications of Hubble rates. These figures show the abundances of helium-4, helium-3, deuterium, and lithium as a function of the decreases exponent n and of the initial scalar field's density normalized to the phantom density at 1 megaelectronvolt. The standard cosmological model is recovered with a null density. The dashed line represents the individual Big Bang nucleosynthesis constraints. Except for lithium, the excluded regions are above the line. We can also see that there is no point where the abundances of elements are all compatible with observations. It is like the standard cosmological models. If one disregards the lithium constraints, considering the chi-square constraints with helium-3, 4, and deuterium, we obtain this limit. For n equal to 4, the limit can be reinterpreted as 3 extra species of neutrino. Now, we consider scalar fields with decay into radiation during BBN. The evolution of the scalar field density is given by the Klein-Gordon equation with, in addition, a decaying constant gamma. The rating temperature is defined by this formula. These figures show the evolutions of the decaying scalar fields density, matter density, and radiation density as a function of the scale factor. We can see an increase in radiation density, which corresponds to the rating. Considering the evolution of this density, it is possible to make theoretical predictions for Big Bang nucleosynthesis. These figures show value of helium-4, helium-3, lithium abundances as a function of the rating temperature for n equal to 3, 4, and 6. The dashed lines represent the chi-square constraints by thinking as expected. Finally, for a decaying scalar field, The observational constants give this limit. To conclude, we have seen that fuzzy dark matter behaves as dark matter. K-source model has dark energy, and that is possible to have a single scalar field replacing simultaneously dark matter, dark energy, and inflation. Furthermore, we have derived constants and stable and decaying scalar field from Big Bang nucleosynthesis. So, thanks for your attention.
Yeah, thank you, Jean-François. Other questions? Please use your raise hand feature. You mentioned tensions in theoretical predictions and experimental measurements of the lithium abundance. So I wondered, did you want to convey here that with this triple unification model, you can also try also make a shift in the prediction in the theory that is aligned with the prediction, or is this beyond this model?
Actually, with this model, we have seen they cannot be agree with the constants of lithium-7, as we can see here. So in this case, it's for general scalar fields, though it is the same for the triple unifications.
It's not a quadruple unification model. You get one extra. If you think of other measurements, for example, measurements where you look at the volume power factor, that can also give you some tests of this model.
Test the triple unification models?
Yeah.
Actually, to test it, we can test with a cosmological microwave background by putting some limits on lambda, as we already seen for fuzzy dark matter models. So it puts some limit on lambda. So we could study the constant in low density after CMB or for galaxy formations, but it reproduces the fuzzy dark matter model. So if we test the fuzzy dark matter model, we test the triple unifications actually. And if we test the Starobinsky inflations, we test the triple unifications. So in this sense, we can test the triple unification by part. In this case, we have this behavior, we can test it, and so on. And the same for dark energy, actually. And we here, where it is, sorry. Yes, here we could test the potentials, for example, if V is small, but as there are constraints on V, but we could increase this constraint for measurements if we have a disagree with the model, actually. So we could test the triple unification via the potential, but it's not the only possibility to do the symmetry breaking, actually.
Okay, thank you. I don't see any raised hands, questions in the chat. So thank you, Jean-François, for your talk. And we come to the next talk, which is by Achille
Arthur.
Yeah, I hope I pronounce this correctly.
Yes, it's Nicola.
Yeah, hello.
Try to
Can you share your screen? Yeah.
Okay. And hello?
Yeah, we can hear you.
Okay, excellent.
Make it full screen.
Yes. Do you hear now?
Yes, this looks good. Thank you.
Okay, excellent. All right. First of all, good morning, everyone in Prague or Europe. I would like to thank Marcus, first of all, and also the speakers of this session for accommodating my, a very short notice request and for rescheduling this talk. Okay, so what I will be talking about is something which we are doing with my students here in Sydney, and this concerns about monopoles within the electroweak sector of the standard model, so-called electroweak monopoles, and their role in electroweak baryogenesis. All right, so I want to start my talk with the question, what is the next energy scale to be probed in particle physics? And this is, of course, a very important question, especially now when we do not see at colliders any anticipated before evidence for new physics. If you look carefully at what we have at hand, the evidence of the standard model, the first one is, of course, the neutrino masses. And so what you can do without any prejudice about the neutrino masses, just taking the fact that the neutrino masses exist and writing down them in the standard model Lagrangian, then the usual way to judge whether this theory is correct or not, or applicability of theory, is to extrapolate this to the high energies. And you know that if you compute, for example, these diagrams of neutrino scattering with the production of longitudinal electroweak bosons, you will find out that the unitarity of the theory is violated somewhere in 10 to 11 GeV. So incidentally, this is very close to the neutrino seesaw scale. So very, very high scale, which we can't presume to probe in any visible future at colliders. No, another evidence for this physics beyond the standard model is, of course, dark matter. This is not, from the particle physics perspective, this is not that robust evidence because it involves only gravitational interaction. However, if you assume certain type of dark matter, so-called WIMP dark matter, or thermally produced weakly interacting standard model particles, and then you can deduce that their abundance are related inversely proportional to thermally average cross-section. And this cross-section has also bounds, unitarity bounds, which gives you a bound on the mass of the WIMP particle, which is less than 100 TeV. Again, that is possible to detect at LHC in principle, but we do not see any evidence of WIMPs yet. And of course, the WIMP is only one corner now of the dark matter paradigms. There are many other models. So in fact, what you want to argue is that the next scale, which is interesting to probe, is actually around the corner. And this is related to the non-perturbative effects in the standard model. And in particular to the Sphaleron transitions. Now we know that gauge sector of the standard model, or the electroweak sector, has non-trivial vacua, and the transition between these two vacuas can occur because of the electroweak instantons. And there are various processes, exotic processes associated with these transitions. In particular, there are P minus baryon and lepton number violating processes by 3 units, et cetera, et cetera. Now, however, being non-perturbative, these processes are extremely suppressed, at least at energies we know. And the barrier which gives this suppression, now for quantum tunneling, is about 10 TeV. So this is roughly a so-called Sphaleron mass. So in principle, if we can overcome this barrier, we would see very interesting physics. And this is presumably the next scale to be probed in particle physics, assuming that we can probe it. Now, so there is certain questions about the accessibility of this scale, and these questions are related exactly to what I said, but I will return to this in my talk. Now, what I want to talk about quickly about the monopoles by itself, the magnetic charges. And just this slide to remind you that the Maxwell's electromagnetism is a triumph of symmetry in physics. It embodies relativistic invariance, and through that, it gives a common description of electric and magnetic phenomena. And of course, there is still not quite symmetric distribution of electric and magnetic charges, prediction of electric and magnetic charges within the standard model. And in particular, standard electromagnetism does not predict electric charges and the currents. So as you know, back in the 30s, Dirac proposed more symmetric formulation of electromagnetism, by including magnetic charges as well. And the symmetry of these equations now are enhanced. As you can see, because of this, there are extra duality symmetries of exchange of electric and magnetic fields and electric and magnetic charges. If you assume that magnetic monopoles exist. But there is a price to pay for that of magnetic monopoles, at least in electromagnetism. You have to introduce something what we call singular potentials, so singular vector potential, for example. This is known as a Dirac string. However, what was pointed out by Dirac is that the singularity in the vector potential, which is not observable quantity, is not a problem. And moreover, if you assume that this configuration exists, that means the magnetic monopoles exist, then we have, from the quantum perspective, we have the explanation from the quantization of electric charges. This is the famous Dirac quantization condition. Now, so this looks like a very interesting object, of course, and is certainly theoretically possible. The only problem, of course, with monopoles in the electromagnetism, the Dirac monopoles, is that if we compute the energy of the configuration, of the monopole configuration, we see that the energy of the monopoles, which is static energy, which is essentially the mass of the monopole, are divergent for very small scales when R goes to 0. And this divergence means that the theory of electromagnetism has to be somehow regulated at very, very short scales in the ultraviolet if we believe that to the existence of these magnetic charges. Now, back in the 70s, though, Polakov, suggested a variant of this regularization by embedding, for example, U1 gauge theory into the non-abelian SE2, which is spontaneously broken down to U1. And you all know that there are, again, the configurations which at large distances look like exactly as a Dirac monopole. However, at small distances, they are regulated. And so you have this mass of the monopole or energy of the monopole, which is quite close to the similar to the energy of the monopoles, the sphalerons I mentioned before. Now, another thing about these Polakov monopoles is that they are stable configurations. This is very important, and the stability of this configuration, as you know, are ensured by the non-trivial topology. The second homotopy group is non-trivial in this particular case. So if we have this situation, this type of monopoles then of course, and in cosmologically phase transitions, corresponding phase transition, then the monopoles are not anymore optional. They are kind of mandatory. They will be produced, and because of the stability, they will stay around today. Now, however, of course, the standard model is not, electromagnetism is not just U1 theory, we know that. And of course, in the standard model, we don't have just SU2 theory and the triplet scalar. Instead, we have SU2 U1 electroweak gauge group, which is spontaneously broken down to U1 electromagnetism. And by the Higgs mechanism, and the Higgs field here is, of course, the standard Higgs field, which is electroweak doublet. Now, so for a long time, it was believed that because of this particular situation, because of this particular vacuum manifold of the Higgs field, there are no topologically stable monopoles within the standard model, within the electroweak theory. But this turns out to be plain wrong, and let me try to explain why is that. So the usual, argument why the topology is trivial for potential monopole solutions in electroweak theory is the following. So if you take now the vacuum manifold of the Higgs field, it's given by this equation over here, and so it represents now 3 manifold rather than 2 manifold in the Hopf-Polyakov model. And therefore, if you want to wrap two sphere, which is the boundary on spatial infinity, onto the 3 sphere, which is a vacuum manifold, of course, this wrapping is trivial. And therefore, that was the usual assumption that there are no stable electroweak monopoles within the standard model. However, in the middle of 90s, Cho and Mason proposed the ansatz and the solution for the monopoles, electroweak monopoles, which is some kind of mixture between the Hopf-Polyakov and the Dirac monopole. So it's a singular ansatz, and it's given in certain gauge here. The H is the Higgs field, A is the field gauge field, triplet of the gauge fields of SU2, and B is hypercharged gauge field. And you can see that at theta equal pi over 2, there is a singularity both in the Higgs field and in the gauge field configuration. Now, so this reminds us that it contains also kind of a Dirac construction. So that singularity is basically what prevents this typical argument about the triviality of the vacuum manifold in the standard model, because, for example, if you have a 3 sphere and you pinch it, it's topologically not anymore 3 sphere, but something else. So to see what it is, you can work with this complex coordinate in the field space and rearrange the potential, taking certain gauge transformation to removing the divergences from the gauge fields, SU2 gauge fields, but they still remain in the Higgs field and the B fields. So this is the construction which is known as the Wu-Yang construction. So when you define a different fields on the different patches to avoid singularities. Now, however, the transition function at the equator is a holomorphic function. It's just basically exponent to the power I phi, and therefore, by definition, Z1 and Z2 coordinate actually span a projective complex plane rather than 3 sphere, and the projective complex plane, or in other words, Riemann sphere, known in mathematics, is topologically equivalent to 2 sphere, and therefore the vacuum manifold indeed for this type of solutions, the mapping is non-trivial. Now, of course, okay. Of course, if this is true, then we have this kind of topologically non-trivial vacuum monopoles, electroweak monopoles, and these monopoles mediate so-called baryon number and lepton number violating processes similar to the sphalerons. Actually, if you look very carefully in the configuration of 2 monopoles, they can form the bound state, which reminds very much sphalerons. Okay. So now we know from one hand that the monopole particle scattering is unsuppressed. This is a particular effect known as the Rubakov-Galland effect. And so one can assume also by just crossing symmetry that also the production of the monopole-anti-monopole pair will be also unsuppressed. So this is something which is a very generic argument. However, it needs to be verified by calculations, of course. So the claim here is that it might be that indeed we can produce this monopole anti-monopole pair without exponential suppression, which I mentioned for sphalerons. Now, another important effect of the existence of these monopoles is yes. Oh, I don't see actually the timing. Marcus, can you tell me how much left for me?
I think you have about 10 minutes left, if I'm correct.
All right. Thank you. So another important effect, which is which comes with these monopoles, electroweak monopoles, is the extra theta phase or the CP violating phase, which can appear in the electroweak theory. And this phase is actually, you have presumably familiar with this phase in the axion physics or strong QCD CP problem, but usually it's believed that in electroweak sector, these theta phases can be removed by the rotation of quarks, by the redefinition of quarks, the phases of quarks. But this is not true if you have the monopole in your sector, and in particular, something what we will call theta electroweak remains in the spectrum, which is the physical phase, which is the difference of theta terms of the SU2 and hypercharge fields. Now, of course, this extra CP violation will have some effects and contribute to EDM of known particles through the exchange of monopoles. However, these processes for the monopoles we are discussing are quite suppressed, so there are no constraints from there. But another thing is that the existence of these monopoles now since we established the violation of P and L, baryon number, and the extra source of CP violation may lead to a successful electroweak baryogenesis. Now, before I go to the baryogenesis scenario, let me talk about the monopole mass. Again, if you just remain within the standard model, since this construction reminds the Dirac construction, the monopole mass is infinity. So one needs to regulate that in a certain way. And so we considered string-inspired extension of the standard model, where the, say, hypercharge field or SU2 are written in a Born-Infeld form, the kinetic term for those fields, and have considered the various constraints which are coming from the nonlinear, say, electromagnetism, which is induced by this Born-Infeld parameter beta. Now, first of all, you can regulate by this nonlinearity the monopole mass, and the monopole mass is now given like this. And the constraints on the beta parameter from the nonlinearity in the propagation of light gives the monopole mass of about 3 TeV. However, later on, Ellis and Mauro Mados and you have pointed out that data from LHC actually on the light by light scattering on constraints this parameter even. There are even stronger constraints on this parameter. So the monopole mass today constrained from the observations is about 10 TeV. So if you want to produce these monopoles at colliders, you need at least, since they are produced in pairs, you need at least 20 TeV collider, okay? Now, let me discuss now the baryogenesis scenario of these monopoles. So here, you are all familiar with the three conditions for the baryogenesis to occur dynamically in the early universe. One is the violation of baryon number, and the C and CP violation. And if we are talking about electroweak baryogenesis, we need some type of departure from thermal equilibrium. And that could be provided by if the electroweak phase transition is of first order. Now, in the standard model, we know that the baryon number violation are mediated by sphalerons. C and CP is violated through the CKM matrix. but the departure from thermal equilibrium is not first order, okay? So now, if there are monopoles also in the electroweak sector, we have additional violation of baryon number mediated by monopoles, additional CP violation through the electroweak theta phase, and I will argue that also the production of monopoles induce strongly first order phase transition. So how the monopoles are produced? Well, this is a typical story. We have through the Kibble mechanism in the early universe. So we have the phase transition happening, electroweak phase transition with the bubbles of new phase expanding in the false vacuum. And it could happen that some topological defects can form while this phase transition takes place. And the core of these topological defects can describe the core of the monopoles, in fact. So one can, of course, the calculation of density by production of monopoles is very complicated, but as an order of magnitude estimation, you can estimate this like this. So if you have a 10 to 7 GeV mass monopole, then the density is 10 to minus 26 per cubic centimeter. All right, so these monopoles are produced during electroweak phase transition, and at the same time, what they do, they distort the second, smooth transition, the so-called of electroweak, usual electroweak phase smooth transition, and induce deviation from thermal equilibrium. So the energetics of this transition, you can looking at the critical temperature and the value of the Higgs field at the critical temperature. So the energetics tells you that the Gibbs energy, free energy, which is actually the thermal potential at the origin and at non-zero VV, thermal VV of the Higgs field, has to be equal to each other. But now, since we have also production of monopoles, there is the extra energy cost to produce those monopoles. And of course, if we estimate the density of the monopoles are very massive, and they are non-relativistic particles. So the density multiplied by mass is actually the energy density of the monopoles. And so you can solve this equation for the mass versus Fc of a TC, which basically gives you a strength first order departure from the smooth transition. And if Fc of a TC is bigger than 1, then you see that the transition is actually strongly first order, in a sense that the Falaron processes are ineffective in the program phase. So if we have the production of baryon asymmetry, it won't be washed out later on. Now, so for this to happen, the mass of the monopole has to be quite heavy. So you need a large density in here. And so it should be bigger than this number. Now, of course, the density of monopoles cannot be arbitrarily large because there is a constraint from the BBN, the usual constraints from BBN. The monopoles should not dominate the BBN era. And the constraint from there comes on the mass of the monopoles and equal to 2.3 10 to 4. Now, of course, there is a large uncertainty in these calculations. However, it's quite amusing that it narrows down to a very, very narrow region of potential region for the monopoles which work for baryogenesis. Now, again, I'll remind you that we have a non-zero theta phase, which is in this particular case, in the presence of monopole in the electroweak sector. And And so we have essentially all ingredients to generate non-zero baryon asymmetry. And, we can set up the very simple Boltzmann-like equation for the baryon asymmetry. So the production of each baryon would correspond to the CP violating process, which goes with the monopoles. And this Boltzmann equation can be solved very in a simple way. And of course, everything depends on this linearly on this theta CP violating parameter and the density of initial density of produced monopoles. And so we can express later on everything in terms of a critical temperature, fine structure constant, and this CP violating parameter. And of course, you can tune the CP violating parameter, since this is not constrained at all so far, to be 10 to minus 10, 10 to minus 3, 10 to minus 2, in order to reproduce the desired asymmetry in baryons. Okay, so you can generate quite naturally the baryon asymmetry through these monopoles. Okay, let me go to my conclusions now. That the first thing is to try to convey the message that the electroweak monopoles are inescapable prediction of the standard model. And there are very interesting physics behind of this once you accept that. First of all, there is electroweak extra CP violating phase just in electroweak theory, which is known as the electroweak CP theta term. Then, of course, there is very interesting physics associated with the light monopoles, which should be larger than 10 TeV, as I argued, because there is the particular spectacular processes of multi-particle processes with delta B, delta L equal to 3 violation in the collision, for example, of protons. But at least you need the energies to probe these monopoles. At least you need the energies with the current constraint. You need the energies bigger than 20 TeV. And finally, if you have heavy monopoles enough, around 10 to 7 GeV, they can drive the first order electroweak phase transition and to guarantee you successful baryogenesis. Now, these heavy monopoles presumably need to be looked in astrophysical experiments. Thank you very much.
Thank you, Achil. Other questions? Please use the chat or raised hand feature. Here on the last slide, you mentioned astrophysical experiments. Is this referring to the possibility that these electroweak monopoles could be a contribution of dark matter or a strong contribution of dark matter?
Oh, that's a very interesting question. Well, what I was referring actually is that you can, well, I mean, the monopoles, you know, produce, of course, non-relativistic, but these mass monopoles, which are actually the, you know, what is called the middle range masses of the monopoles are quite, you know, they are accelerated very rapidly in magnetic fields. So they are relativistic. So they produce, for example, Cherenkov radiation, right? And so you can detect in principle those events in ICECube, say, or in cosmic rays and things like that. So this is what I meant, astrophysical observation. Of course, there are limits on already existing limits on this, but if you believe in the picture which I was talking about, the fluxes are still small. If you can compute the flux of the molecule, still small. So this is still presumably awaits its discovery. Now, the question of dark matter is extremely interesting as well. And now I don't have a qualitative answer to these questions, but I think the fluxes, if you believe again to the baryogenesis scenario, fluxes are too low to account for the whole dark matter.
But yeah, so I'm familiar with measurements at neutrino telescopes. Also, the non-relativistic monopoles can be even more interesting if they induce proton decay via this Kallan-Rubakov effect that you mentioned. So
yeah,
we would a secondary Cherenkov emission and a slow chain of Cherenkov bursts as the particle crosses the detector.
Yes, that's exactly. I mean, there is a lot of things that are going on, and there are some particular things with the electroweak monopoles. So, for example, electroweak monopoles do not induce a proton decay. Okay, So they do not induce proton decay. However, they induce the processes baryon and lepton number violation. So since they do not induce the proton decay, you can avoid a lot of bounds already existing. But they still, induce a very, secondary radiation, as you mentioned, this through this multi-particle processes, right? So yes, I mean, this is something very interesting to look at. Yeah.
I was confusing this with gut monopoles. Yeah.
Yeah,
Right.
yeah. So there is a particular differences there with the gut monopoles, but yes, indeed, in general, this is an interesting to look at.
Okay, I don't see any other questions or raised hands. Then, Achel, thank you very much, and also thank you to the other speakers of this block. And we have now another coffee break for 30 minutes. We are going to reconvene at 20 minutes to 12. See you soon.
Thank you.
Hi, Francesca. Are you still on the call? Okay, never mind. Talk to you later. Francesca, I see you now. Do you want to test your audio?
Yes, please. Hi.
Yeah.
So.
And yeah, so I can hear you. And do you also want to?
I try. Yes.
Yeah. That already looks good. Maybe if you do full screen.
It's not in full screen.
I mean, it's almost full screen. It's acceptable.
It's strange. However, in my screen is full screen. So.
Yeah. So yeah, it's fine. There's just, you know, like a toolbar on top, but that shouldn't be any problem. That's fine.
I can try again just in case. I don't know. It's the same.
It is the same.
Yeah.
Francesca, when you share your screen, it offers you different windows. Try out the full desktop sharing.
Yeah.
The full desktop instead of the specific.
Exactly. Yes, the full desktop. That's what works.
I see. So I stop sharing. Share the screen. Whiteboard? No.
No, it's not the white.
Ah, the desktop one. Yes, now I see, maybe. And then this way.
Yeah, perfect.
Okay, thank you very much.
Good morning, Francesca.
Ciao.
Ciao.
Thank you for your suggestion.
Hi, Jia Hui Y.
Yes. Yeah.
I just saw your message, your private message. If you want, you can quickly test
Okay.
your screen. The audio is working already.
So did you see it in full screen?
Yeah, I think something. Yeah, I see.
And the
it.
laser pointer is working also.
Yes.
Okay,
Yeah.
thank you. Great.
Yeah, thanks. I see that Francesco is also on the call. Do you also want to test out your screen sharing? I see that you have not submitted your talk to Indico, so I won't be able to share the screen for you. Francesco, are you there? I see that your mic is open, but I cannot hear you. Okay, maybe we can sort this out. Maybe we can.
Okay, good morning. Can you hear me?
Now I can hear you. Yeah. Okay.
Okay, good morning. Sorry for not uploading on Indico. I will try to do it now.
Yeah, you still have time.
Okay, I can try to share, do a test of sharing now. Can I do a test now of my sharing?
Yeah, you can. Yeah, if please go ahead.
Okay. Can you see it full screen?
Mm-hmm.
Okay, cool. Okay. Thanks. I will try to upload it in the meantime.
Good, thank you. So yeah, welcome back to the session. If you are joining us for the first time, please use the raise hand option in Zoom if you want to ask a question at the end of the talks. Or you can also post your question on the Zoom chat or the MetaMost chat, and Alexei will send you a reminder about the link during the talks. And so we changed topic now. In the third block today, we are going to hear about recent measurements of AMS on board the International Space Station. And the first talk is by Francesca.
Okay, I'm going to share my screen. Do you see it?
Looks good.
Okay, great. So, hello everybody, I'm Francesca Giovacchini from CMAT, and today I'm going to present on behalf of the MS02 collaboration the properties of cosmic helium isotopes measured by the alpha magnetic spectrometer. Okay, so the cosmic rays are commonly grouped in two categories. Primary cosmic rays, ionized nuclei like proton, helium, carbon, and oxygen, which are produced and accelerated at their sources, like supernova remnants, and they propagate through the galaxy before eventually enriching us. This energy spectrum of the primary cosmic rays provide information on the injected spectrum at the source and on the propagation processes that these cosmic rays went through during their journey in the galaxy. The secondary cosmic rays, like lithium, beryllium, and boron, but also deuterons and helium-3, are instead produced by the primary cosmic rays in their collision with the interstellar medium. Their energy spectrum depends on the energy spectrum of the parent elements, so the primary cosmic rays, and on the propagation process through the galaxy. Therefore, the secondary to primary flux ratio, like lithium over oxygen, beryllium over oxygen, etc., factors out the source spectrum of the progenitor and provides information to constrain the transport parameter in the propagation models. And the knowledge and understanding of the propagation of cosmic rays in the galaxy is important not only by itself, but also in the search of new physics, in order to model the background and be able to significantly disentangle the new effect, the extra signal with respect to the background. And AMS provides precise measurement of both primaries and secondary cosmic rays, like you will see from my colleagues in the presentation of tomorrow. And the helium isotopes are a special case of these secondary and primaries species. The helium in cosmic rays are the second most abundant nuclei, consisting of two isotopes, helium-3 and helium-4. The helium-4 is thought to be mainly produced and accelerated in astrophysical sources, so is a typical primary. The helium-3 is mostly produced by fragmentation of the helium-4, so is a typical secondary. The distinct origin of these two isotopes, so helium-3 secondary and helium-4 primary, and the single fragmentation channel in the production of the helium-3 from the helium-4 allows a simpler comparison with the propagation model with respect to heavier secondary to primary nuclei ratio like boron over carbon and boron over oxygen, where the lithium, beryllium, and boron are produced by multiple fragmentation channel from many heavier nuclei that interacts with the interstellar medium. In addition, the small cross-section of the helium with respect to heavier nuclei allows the helium-3 over helium-4 flux ratio to probe the properties of the diffusion at larger distances, sampling larger volumes to any other secondary to primary ratio. And it also allows to test the universality of the propagation for different A over Z. With AMS, we measure the flux of helium. We published this measurement in 2015. Here I show you an update of this measurement based on 125 million helium events collected during the first 6.5 years of data taking. In this plot, the AMS measurement in red are together with the most recent results from other experiments and plotted as function of the kinetic energy per nucleon. As you can see, the energy range of our measurement is wide and range from the fraction of JeV up to the TeV, with the percent level precision around 100 gigavolt. The cosmic rays, which are arriving at the heliosphere, are expected to be subject to variation, which depends on the solar activity. And with the AMS, with these large acceptance, high precision detection capabilities, and the long mission duration, we measured and published the flux of helium as a function of time in the region between 1.9 and 60 gigavolt from May 2011 to May 2017 covering 29 Barter rotation over solar cycle 24. Here I displayed in 5 selected rigidity bins, where you can see that at low rigidity, the flux of helium is not time independent. Instead, we see variation in time, and the amplitude of this variation decrease with increasing rigidity. And about 1 year after the solar maximum, we also see that the flux steadily increases. AMS is a precision multipurpose spectrometer operating in space at 400 kilometers orbit. Is made of several specialized subdetectors for a redundant particle identification. The helium nuclei are identified by their charge, which in AMS is measured repeatedly all along the particle trajectory inside the detector, from the top to the bottom with good resolution. For this specific measurement, we use the measurement of the charge in the layer 1, in the upper time of flight, in the 7th layer of the tracker, and in the lower time of flight. And this results to a negligible misidentification, keeping, however, an efficiency pretty high, above 98%. Using the information of the charge in the first layer on top of AMS, we could also reduce the background due to the interaction of heavier nuclei with charge greater than 2, fragmenting into helium. And we reduce this background to a negligible value of the order of the per mil. In order to identify the isotopes, we measure simultaneously, we need to measure simultaneously the charge, the rigidity, and the velocity of the particle. So for this measurement, the critical detector, the key detector are the tracker, the time of flight, and the reach. The tracker system is made of 9 silicon layers. For this analysis, we do use the 8 layers, the layer 1 and the inner tracker, in order to maximize the acceptance, since our measurement in any case is at low energy. And the tracker is providing a measurement of the rigidity, which is the momentum divided by the charge of the particle, with a resolution of better than 10% at 20 gigavolt. And as you can see, the response of the detector is well reproduced by our simulation. For the measurement of the beta, we have two detectors, the time of flight and the reach. The time of flight is made of two matrices of scintillating counters, located one above and the other below the core of the detector, so the inner tracker and the magnet, and is providing a measurement of the beta of the particle with a resolution of 2% for helium or with beta around 1. In the bottom of the AMS instrument is located the reach detector, which has a dual radiator configuration. At the center, tiles of sodium fluoride, which are surrounded by aerogel. The sodium fluoride has a refractive index of 1.33, which corresponds to a Cherenkov threshold around 0.75, 76, and provide the measurement of the beta of the particle with a resolution of 2.5 per mil for charge 2 and beta around 1. The aerogel tiles has a refractive index of 1.05, which corresponds to a beta threshold at 0.96, and is providing a measurement of the beta with a very good resolution of the order of 0.7 per mil for charge 2 and beta 1 particle. And these three measurements define the true range of measurement and final results, which are in energy partially overlapping. In order to correctly measure the flux of helium-3 and helium-4 in the galaxy, we have to take into account and to correct for the interaction inside our detector. As I discussed before, for what concerns the interaction of heavier nuclei fragmenting into helium, we do take this under control with our measurement of the charge on top of AMS with the layer 1 charge identification, and we reduce this contamination, this background, to a negligible value. The contamination of the in the helium-3 sample due to the fragmentation of helium-4 into helium-3 instead is more complicated, because, as you can see, there is no change in the charge, so it's more complicated to be tagged. But is determined from we can determine it from the direct measurement in AMS of the helium-4 fragmenting into tritium. And this because helium-3 and tritium production cross-section in the helium-4 interaction are expected to be similar and constant at high energy above 0.2 GeV over nucleo, as is supported by the literature. So with AMS, we can measure the isotopic composition of the products of the charge-changing interaction of the helium with the AMS detector. Selecting charge 2 in layer 1 and TRD, and charge 1 in the inner tracker, and looking to the mass distribution of the products of this interaction. And we could, in this way, validate our Monte Carlo simulation with the direct measurement of the experiment. The associated systematic error to this correction is of the order of 1.5% for the helium-3 and 1% for the helium-4. In order to identify the isotopes, we do use a procedure which is using the unfolding of the rigidity distribution. We select a narrow velocity bin compared to the beta resolution, and then we unfold the momentum distribution within this very narrow beta bin, and using the tracker resolution function, we get the helium-3 and helium-4 peaks that now are separated, and we can count the events on top of AMS with already the correction due to the energy loss and due to the acceptance accounted. And then we fold back the results and if we fit to the data in an iterative process. And here I show you the results of this analysis, what we published last year. The flux of the helium-3 and the helium-4 and the ratio has been measured with the very same precision instrument in an extended period of time from May 2011 to November 2017 in 21 periods of 4 Barter rotation each. And you can see on the left the flux of the helium-4 in blue and helium-3 in red for 5 selected characteristic rigidity beams. And as you can see, so for the isotopes, the flux is not time independent, but show structures, and the structures are nearly identical for helium-3 and helium-4. The relative amplitude of this structure is decreasing with increasing rigidity, and going from a factor 2 in the first rigidity beam to about 10% in the last beams, which is shown. In the left plot, I show the ratio of the helium-3 over helium-4 as a function of time for the very same characteristic rigidity beams. And we observe that below 4 gigavolt, the ratio has a transient in its behavior, so before is stable and then start to decrease. And the time of this transient has been estimated to be around the end of February 2015, which is compatible with what we found in proton over helium. And also the structure that you see on the left of the variation, let's say, of the flux as a function of time are in agreement with the same measurement that we perform in positron, electron, and proton. In this plot is shown the flux of the helium-3 and the helium-4 averaging time as a function of rigidity, and the error here are the total error, accounting for both a systematic and statistical. The helium-3 flux, the helium-4 flux has been measured in the rigidity range between 2.1 and 21 gigavolt, based on 100 million helium-4 events. The helium-3 flux has been measured in the range between 1.9 and 15 gigavolt, based on 18 million events. And the shaded region show the range of the time variation. And we also measured the ratio between the helium-3 and the helium-4, again, average in time as a function of the rigidity with total error. For rigidity below 4, the shaded blue area indicates the results of the single power law fit for each of the 21 time periods. Above 4 gigavolt, the green line indicates the fit with the single power law, and we measure the spectral index to be around minus 0.2.94 plus or minus 0.004. The fraction of helium-3 and helium-4 seems steadily decrease as a function of rigidity. And we also check the spectral index stability that seems to be constant, that we observe to be constant above 4 gigavolt, and to be in agreement with the spectral index that we measure in the boron over carbon and boron over oxygen at high energy. In order to compare our measurement with the previous experiment, which were provided only in kinetic energy and never in rigidity, we repeated this analysis also as a function of kinetic energy. And you can appreciate the measurement of AMS, which are extending the region of this measurement to much higher, energy in a region which is was almost unexplored. And here you can see also the comparison with the Galprop model. To conclude, AMS has performed a precision measurement of the cosmic ray helium-3 and helium-4 isotope fluxes and their ratio with rigidity from 1.9 to 15 gigavolt for helium-3, from 2.1 to 21 gigavolt for helium-4, and from 2.1 to 15 gigavolt for the ratio, based on 100 million helium-4 and 18 million helium-3 nuclei. Below 4 gigavolt, the helium-3 to helium-4 flux ratio show a long-term dependence. The helium-3 to helium-4 flux ratio was found being always decreasing with rigidity below 4 gigavolt, following a power law with a delta equal to minus 0.21 plus or minus 0.02 and the time dependence of plus or minus 0.05. Above 4 gigavolt, the helium-3 to helium-4 flux ratio was found to be time independent, and its rigidity dependence is well described by a power law with delta equal to minus 0.294 plus or minus 0.004. The measured helium-3 to helium-4 flux ratio power law spectral index is in agreement with the one that we measure at high rigidity for the boron over oxygen and boron over carbon ratio. Thank you for your attention.
Yeah, thank you, Francesca, and congratulations on these nice AMS results.
Thank you.
So the floor is open for questions, and please raise your hand or write something in the chat if you have a question for Francesca. Yeah, I see that Monica.
Yes.
Also a question.
So I have a question. So the proton over helium also decreases. So the explanation is it's due to the isotopic composition of helium with what we saw today, or we cannot conclude that yet?
No, it's not connected to, we don't believe it's connected to that. We believe that it's connected to rigidity, let's say, to dependence due to the different charges so far, but we don't have conclusion.
Okay, so because here there is also this decrease in the flux ratio, it doesn't mean it explains the proton to helium.
Not so, we don't have conclusion so far, let's say.
Okay, thanks.
Are there other questions? I had a more or less technical question. If you go back to slide 5, so on top of solar modulation, you also see some sort of modulated structure on smaller time scales, like half a year. Can you say something about that? Is this related to solar activity, or?
Yes, there are some connection with the solar activity that has been studied specifically for the proton and helium, and we do have also now the study for the daily to see if it really. So we have ongoing work which is also more detailed in time to be associated to activity in the sun. Yeah, so it's really.
There's some physics behind that.
Physics, right.
Thanks. Okay, I don't see any other hands up. Okay, then thank you, Francesca.
Thanks to you.
And let me see who's next. So We come to the presentation by Jiahui Wei.
Yes, hello.
Hello.
Okay, I'll start sharing. Let's see. Yeah, can you see it properly?
Yeah, I think some. We see the presenter screen.
Okay, I see. So I will go back. Just.
Yeah, this is better. Yeah.
Okay, great.
We also see your cursor.
Yeah. Okay, so good morning or afternoon. I'm Jiahui Wei from the University of Geneva. So today, on behalf of the AMS collaboration, I would like to present to you our measurements on the like nuclear isotopic composition in the cosmic rays using AMS. So as we have presented that with AMS-02, we have intensively measured primary and secondary nuclei fluxes, which has been covered by a talk on Tuesday. And this measurement of nuclei fluxes has provided important information to understand the origin and propagation of cosmic rays. And furthermore, we can get additional information from the isotopic composition of this nuclei. So for example, the isotopes may have different origins, like in helium and proton and deuteron, that one of the isotopes is secondary and the other one is mainly primary. So this topic has been covered by the previous talk on helium, and you will hear another one in the following talk. And isotopes may also have different propagation history. A good example of this is beryllium, where beryllium-7 is an isotope with short lifetime, but beryllium-9 is a stable one, where beryllium-10 has a lifetime of around 1.4 million years. So that is compatible to the time residence time of beryllium in the galaxy. So that makes beryllium isotope a so-called radioactive clock to study the propagation history of cosmic rays. Another interesting topic is about lithium isotopes, where the lithium-6 and 7 are supposed to be mainly primary, secondary cosmic rays, so that they are determined by the secondary production cross-section from carbon and oxygen. But the measurements of these two isotopes may also be used to test the presence of primary lithium in cosmic rays. So this I will explain in more details for the following talks. And so for this presentation, I will focus on lithium and beryllium isotopes, where we develop isotopic composition measurements with MS. So before I go to the measurements, let me have more remarks on the two nuclear isotopes. So for lithium, there are two recent cosmic ray propagation studies which use the AMS, lithium, beryllium, and boron data to perform a global fit. So as you can see in these two publications, they found some tensions in the lithium fluxes, where the data shows to be higher than what we expected from the model. So on the right, you can see an example from one of these papers. So this dash and dot line is what expected from the model. And the red line is after considering the time period of AMS data taking to account for the solar modulation. And you will see a model expectation like this, where the point is the AMS published data, and you can clearly see the tension at this part. So that both of the two studies proposed different interpretations for this difference. So in one of them, this is interpreted as uncertainty in the lithium production cross-section. And in the second one, this is interpreted as a contribution from primary lithium. So if we add primary lithium to these models, so you will find another red line here, which is compatible with AMS data. So that the measurements of lithium isotopic composition may help to further investigate this tension, as the primary lithium is expected to be lithium-7. So the next page is on the beryllium isotopes. So as I presented, the beryllium-10 can be used as a radioactive clock. So as you can find in these two recent studies, this illustrates how we can use the beryllium-10 to beryllium-10 to boron-10 decay to study the propagation models. So this is one of the example from this paper. So the points is AMS data of the flux ratio of beryllium to boron. So in the model, if beryllium-10 is assumed to be stable, so you will get this dotted line, which is much higher than what we get from data. So if we take into account the decay from beryllium to boron, you will see these several lines, which is for different parameters. That is for the galactic halo size. And so this increasing at this energy range can be explained that below a certain energy, below certain energy, the escape time of the beryllium will be longer than the decay time. So you will see a constant increasing of the ratio of beryllium to boron. So with this method, you can already constrain these parameters, but this method is limited by the cross-section of the splashing from beryllium to boron. So to further constrain the models, a more direct way is to use the beryllium-10 to 9 measurements. So with this, the unstable isotope to the stable isotope ratio, you can directly have a better understanding of the lifetime of cosmic rays in the galaxy. And with this information, this can further help to discriminate between different propagation models and further to constrain the parameters in their model. So with AMS, we are able to extend this measurement of beryllium-10 to 9 to around 20 GeV. So then I would go to the measurements of the isotopes. So with AMS, to identify the incoming lithium and beryllium, we will use the charge measurements by the first layer of our tracker and the upper part of time of flight and the inner 7 layers of tracker and the lower time of flight. With this independent measurements, we can achieve negligible charge confusion. So with this lithium and beryllium data, we can then identify the mass depending on the rigidity, which is defined as momentum divided by charge measured by the inner part of the tracker to have a larger acceptance. And the beta measured by in different energy ranges, the time of flight, the rich sodium fluoride, and the rich aerogel, which covering different energy ranges. So from the rigidity and the beta resolution, we can calculate the estimated lithium mass resolution. So as you can see here, the mass resolution for both of the 3 independent measurements is around 1 atomic mass unit. So that means we cannot reach event by event identification. Therefore, this isotopic abundance will came from the fit to the shape of the mass distribution. And here you can see it's the same situation for beryllium, that the mass resolution is larger than 1 mu. So to build this mass template for the fits, we reconstructed the mass from the beta resolution and the rigidity resolution models obtained from Monte Carlo simulation. And then the systematics in this mass template is implemented by varying the beta resolution and rigidity resolution models with several Nielsen parameters, which account for the shifts, the width of the shape, and the tails. So therefore, we will build one template for each isotope in each energy bin for each analysis. Then to get the isotopic abundance, we perform the global chi-square minimization with bin-to-bin correction introduced for the nuisance parameters. So here is a definition of chi-square, and here is how we perform the global fits. So here in this formula, this C stands for the abundance of isotope A in a certain energy bin, and this nu is for the nuisance parameters in each energy bin. And they describe the uncertainty of the shape of beta and rigidity resolution functions. And the covariance matrix is chosen to take into account the correlation between bin to bins. So after performing the global fits, we will obtain the abundance. So here are 3 examples. That is the lithium isotopic abundances get for the 3 independent beta measurements. And here the errors on the abundance has included both the systematic and the statistical error for the mass, where the systematic error is from the mass template. And also we can apply the same method to get the beryllium isotopic abundances. And we noted that for beryllium, a larger challenge is that the beryllium-10, which we are interested in, is actually the least abundant one of the 3 isotopes. So with this relative abundances, we can then calculate the isotopic fluxes for each isotope. So here is an example of lithium 6 and 7, where the flux is computed from the abundances and the effective acceptances and the exposure time introduced by the geomagnetic field. And then we should correct it for the contamination from fragmentation of heavier nuclei, since lithium and beryllium is less abundant by than carbon and oxygen, and they can contribute a large amount of fragmentation background. And then we fold the fluxes to correct for the energy migration due to the finite beta resolution. And on the right, you can see the lithium fluxes in different energy ranges, where the 3 analyses both have some overlapping region for cross-check. So then we can compare these measurements with previous experiment. As you can see here, is compatible with the previous measurements. And for the first time, we measure the lithium and lithium isotopic fluxes above 0.3 GeV per nucleon. And from this isotopic flux, we can then calculate the isotopic flux ratio from the feed. And again, in the 3 energy ranges, and then put it together and compare with the previous measurements. So here you can see the previous measurements is below 1 GeV per nucleon, and we extended about 1 GeV per nucleon to around 10 GeV per nucleon. And it's consistent with the previous measurements in the low energy part. And similarly, this is the results for beryllium isotopic ratio. And we extended these measurements to around 10 GeV per nucleon. But please be noted that this result, we need further analysis on the background subtraction, since beryllium is the least abundant isotope below charge 8. And then we also perform this isotopic flux measurements as a function of rigidity. So to get these measurements, we use different binning as a function of kinetic energy for the 2 isotopes to get the same rigidity binning. So we will perform the previous introduced analysis methods to get the fluxes for the 2 sets of bindings, and then we convert it from kinetic energy per nucleon to rigidity to get the flux for each isotope. So here the 2 isotopes are displayed, where this lithium 7 has been multiplied by a factor of 0.5 to avoid overlapping with each other. And from the flux measurements, we can then get the isotopic ratio. And here is the result of lithium 6 to 7. And we put also together with the AMS01 measurements. So we have consistent result. And for the first time, we measure this flux ratio to around 20 GeV. So in conclusion, the isotopic composition measurements of like nuclei in cosmic ray is a key measurements to understand cosmic ray origin and propagation. So here in AMS, we presented dedicated method based on template fit of the mass distribution. And the following preliminary AMS results have been presented. So we presented the first measurements of lithium-6 and 7 fluxes as a function of kinetic energy per nucleon, about 0.3 GeV per nucleon, and as a function of rigidity from 2 to 20 GeV. And we also presented the first measurements of lithium-6 to 7 ratio and beryllium 10 to 9 ratio, about 1 GeV per nucleon. So in the future, we would like to further refine the measurements of lithium and beryllium, and we will probably extend these measurements also for boron isotopes. So thank you for your attention.
Thank you, Joey. Yeah. So the floor is open for questions. So also here, congratulations on your new results, and I'm looking forward to your PL publication. I was actually wondering, are you also, so you mentioned the global fit, which requires knowledge of this bin-to-bin correlation matrix. Is this information that AMS also is planning to share outside the collaboration in the future?
I'm sorry, what do you mean, share which part?
So the bin-by-bin correlation matrix that you for the global fit, I think this is not published, is it? I mean,
no, this is not yet.
Yeah, I mean, you mentioned various studies that are fitting secondary to primary ratios.
Mm-hmm.
I guess these studies from external collaborators.
Yeah, these are from external collaborators.
Yeah, so maybe this would be something to think about.
Yeah.
So I don't see any raised hands otherwise, or questions in the chat. Okay, then thank you, Jahui.
Okay, thank you as well.
And we come to the last presentation today by Francesco. Hi, Francesco.
Good morning to everybody.
Good morning. Oh.
Good afternoon. Yes, till morning. Okay, I will share my slides. Okay. Can you see them?
Yes, please, you can start.
Okay. So good morning. So good afternoon or good morning to everybody. So I'm Francesco Di Miccoli from ENFN TIFPA institution, and it's my pleasure to be here to talk on behalf of MS02 collaboration to one particular measurement of MS02 on the ESS, the one regarding deuterons and deuterons over proton ratio. So as introduced by my colleagues before, from 2011 to 2018, MS provided many fundamental measurements in cosmic ray physics. And among all these studies, in this talk, I would like to concentrate on the nuclei of secondary origin. So they were already being introduced. So very fast, they are produced from collision of primary cosmic rays coming directly from the acceleration sites with interstellar medium. They carry information on the history of the travel of the cosmic ray itself through the galaxy and the property of the ESM, and thus are fundamental for the understanding of the origin and propagation of cosmic rays. As said before, the most abundant species in cosmic rays are lithium, secondary species in cosmic rays are lithium, beryllium, and boron, as long as secondary originated isotopes like helium-3 and deuterons. In this slide, I put the status of the secondary cosmic rays measurements before MS in the top part. In the top part, for example, I put the status for two nuclei, lithium and boron. It can be seen the lack of high energy precision measurement in both cases. For the case of the isotopes below, the only measurement is in the extremely low energy range, below 1 GeV per nucleon. Otherwise, you see some measurement with very high uncertainty for the deuterons in above 1 GeV per nucleon. So, as introduced, not only the chemical composition, but also the isotopic composition of cosmic rays is affected by reaction on ESM. Typically, lighter isotopes like helium-3 from helium-4 are produced from spallation of heavier one. The deuterium has a different behavior since the reaction of proton-proton fusion is also important for its production. And it is dominant below the GeV per nucleon of energy. In definitive, deuteron ratio, like deuteron over proton and deuteron over helium, can provide some orthogonal information with respect to the commonly used tools like boron over carbon ratio. So they test different energy ranges and also different propagation distances. And these combined effects are very important, very interesting, as I will show next, for indirect dark matter research. So annihilating particles of dark matter are expected to give rise to excesses in the antiparticle spectra. For example, some deviation measured in the antiproton spectrum are being interpreted in this way. But to do so, it is necessary a very deep knowledge of the yield of antiproton production from standard sources. Also because this is important also because the antiproton are the main source of background for the search of heavy antinuclei, which are far more promising smoking guns of the presence of dark matter in the galactic halo, like for example anti-deuteron or anti-helium. So this is where isotopic analysis can really shine, and in particular the deuterium one is very interesting because antiprotons come from much further with respect to both boron and carbon, which are a test only for local propagation. So like secondary nuclei like deuteron and helium-3 can constrain better basically the antiproton secondary production. This analysis is being performed independently by the 3 other groups in IMS, so we have a good level of cross-check within our collaboration. Very fast, IMS was already presented, so I will just recall you that we need 3 concurrent measurements of rigidity, velocity, and charge to identify an isotope, the mass of an isotope. We use so it's very important to have a good measurement of the rigidity that is given by the combination of what we call inner tracker, so the 7 tracker layers inside our magnetic volume, and the first external layer. And for velocity, we have 2 velocity measuring detector, the time of flight detector active at very low energies, and a Cherenkov detector that we call RICH, that is actually the combination of 2 different detectors, yes, we can say 2 different detectors, one based on sodium fluoride and one based on aerogel. We identify the Z equal to 1 charge with recurrent measurement by all these subdetectors. Okay, I show here some of the peculiarities of this particular measurement, the deuteron one, which is quite challenging. So thanks to its subdetector, IMS can perform the distinction in 3 different energy ranges, which are limited by velocity threshold, basically. A magnetic spectrometer like IMS can better perform isotopic distinction of particle of the same velocity. So the natural units for this measurement would be kinetic energy per nucleon, which is proportional to velocity. The interesting physics effect, nevertheless, are mostly rigidity dependent, like for example, Sauron modulation. And so IMS02 is able to perform give the final result in this variable. But deuterons and protons are the only isotope with very different rigidity at parity of beta, because one is weights double with respect to the other. So calculating the ratio is not straightforward, since as if seen in rigidity, the different energy ranges become quite interlaced with each other. So moreover, the 2 isotopes have different mass, very different masses, so experience a completely different energy loss through MS. So for all this reason, this measurement is quite challenging. We try, for just a few words on the selections. We organize them in 3 steps. As I said, we use layer 1 plus inner tracker, and we choose not to use the last layer of IMS tracker to exploit the acceptance and to have the maximum acceptance possible. And then we define that Z equal to 1 sample with recurrent measurement of charge along the path. And then we have the most important step that assure, with selection, aim to assure a good measurement of velocity. So a set of selection for the quality of the time of flight measurement, and a multivariate analysis for the reach. Okay. This is necessary because in the case of reach measurement, Z equal to 1 means very few Cherenkov photon to perform the measurement. And so we can say a lot of noise. In the central panel of the slide, you can see a typical mass distribution obtained with sodium fluoride. And you can see that is the 2 peaks of protons and neutrons are overimposed on quite a bit of noise. So to deal with this, we develop a completely data-driven multivariate technique to try to get rid of the noise, defining 2 regions in the mass spectrum, one in which signal is expected to be dominant, the green one, and one in which background is dominant. On these 2 samples, we train a multivariate classifier based on the BDT technology, basically, and with a cut on this classifier, we managed to get rid of more than 95% of this background. This is a sample of the situation after this selection, and you can see that we can well distinguish the two peaks, but still the mass resolution is not sufficient for event-by-event identification. So what we do is to fit the mass distribution to obtain the deuteron fraction. To do this fit, since we have basically a signal that is 2 orders of magnitude less than the background, we basically build the templates using Monte Carlo simulation. So the strategy is to fit the mass distribution with the templates from Monte Carlo simulation. We don't use them rigidly, but we allow some level of elasticity on those templates, tuning the velocity response function with a smearing of the time of flight and the measured Cherenkov angle. So in the left plot, you can see a collection of modified templates for protons in red and the deuterons in blue, obtained changing the parameters of the tuning. Among all of them, we choose the one that gives the best mass fit in terms of reduced chi-square. This allows us to optimize the agreement between data and template, and also to extract the systematics associated to this procedure. Okay. So, since IMS is operating since 2011, we have a very big period of data taking with changing condition of solar modulation, which affect the mass distribution. For this reason, we had to include in the simulation also this effect to be able to fit the mass distribution both in period of solar maximum and solar minimum. As you can see in the left panel, including this effect, we managed to have templates which are the dashed line that are able to follow the shape of the proton peak even in different periods of time. So gathering all these, we can finally perform our fit, an example in the lower panel, or adding also the contribution given by the fragmentation of cosmic helium nuclei into the detector into secondary proton, deuterons, and tritium, that are the 3 colored contribution here, which were independently measured with other data-driven techniques. So finally, moving to my result, I show here my results about deuteron flux and our result of deuteron flux and deuteron over proton ratio. Regarding the deuteron flux, we present the results multiplied by rigidity to the power 2.7 to exploit the dynamic of the flux. And the error bar here includes the statistical error and our evaluation of systematics of this measurement. On the top right panel, you can see a breakdown of these error bars, and in particular 2 contributions, the statistical one the red, and the acceptance one show a sudden increase entering the rich, so the sodium fluoride energy region. This is because both because of the reduced statistics, the reduced efficiency of this detector that makes more difficult the measurement, and also the higher number of selections that are necessary, and these increase our systematic uncertainty on the acceptance of the detector. As you can see, our measurement spans from 1.2 up to 19 GeV of rigidity, which is more than 1 order of magnitude more than our predecessor. Last thing is that thanks to the very high acceptance of the IMS, we can try to do this analysis in dependence of time. So in using reduced time binning of 4 months each, we can plot the deuteron and the comparison between the deuteron and the proton flux in particularly interesting rigidity beams. As you can see from the insert on the top, IMS02 is able to span the complete 24 solar cycles, so with 2 periods of solar minimum and 1 period of solar maximum. We are starting to analyze this data, and we are starting to have some small statistical evidence of time behavior of the deuteron over time dependence of the deuteron over proton ratio. These results are very preliminary, but we are starting to see some kind of breakout of the behavior in a time which is correlated with polar flip on the of the solar magnetic field. So in conclusion, isotopic composition of light nuclei, as said before, is a key measurement for cosmic ray physics. We are able to give the first precision measurement of deuteron flux above 1 GeV per nucleon, and we are able to give for the first time a measurement in rigidity for 1 to 20 GeV, and we are having the first hints of low energy time dependence of this ratio, which is still to be understood. So thanks for your attention.
Thank you, Francesco. So are there questions for Francesco? Please raise your hand if you have any. Okay, that doesn't seem to be the case. Everything was clear, Francesco. Thank you very much.
Thanks. Okay.
And so this brings us to the end of this session. We also had scheduled a dedicated discussion session after a short break. But since we are very early, I suggest that we can start this general discussion session right now. So if you have anything that you want to bring up right now, you can do this here in forum. You can also start discussions, of course, in the Mattermost chat. But I guess everyone is exhausted by now and wants to have some kind of food, lunch or dinner or late night snack. Okay, if this is not the case, then we can stop for now. I will stay on the Zoom call, and also the technical support. Jiri is going to leave this Zoom call open if you want to have some discussions also later. And again, I thank you all for your participation, and talk to you later. Bye-bye.
Bye.
Goodbye.